arms. Negotiation stalled and
Baby, yeah.
Honey, Father Doyle stopped by to see how you're doing.
Father Doyle. Should have used Energizer. They keep going and going.
All right, so we get electricity out of a battery, but how do we put electricity into a battery?
In 1987, Stephen Hayes was a young lineman, just 6 months away from completing his apprenticeship. This was a long-time goal for Steve. Like many linemen, he was the third generation of electrical worker in his family. It was on a beautiful spring day when he let his guard down. He was in a bucket truck completing work on a 7600-volt live line, and he removed his protective rubber gloves.
Apparently, there was a failure of a piece of equipment that came down at him that, in reflex, he grabbed, and it was an energized conductor. He had a hand-to-hand contact with electric, and that resulted in internal burning. When you have a flash, you have external burns. When you have a contact accident, it damages the bone marrow. So that's what he had. He had 7,600 volts.
When I made my contact, that was it. I don't remember anything. Apparently, they brought me down, put me on the ground, put the fire out, because I was on fire. It entered through this arm, came through, wrapped around my neck, didn't go up, luckily, into my brain or down into my heart, and went out my other arm. So, I mean, if you're lucky in that kind of a situation, I was pretty lucky. The hospital was rough because the problem with the burn injury, I believe electrical and any other burn, is infection right away. And so they wanted me to make a decision of amputation right away, and it was very tough. I couldn't make that decision up. I mean, I knew it had to be done. I just couldn't bring myself to say, yeah, cut my arms off. It took about 3 days till I came around and allowed them to operate.
Steve would spend 8 weeks in the hospital burn unit. He then endured 3 years of painful rehabilitation, learning to use his prosthetic arms. Then, in 1991, he returned to work, now as an electrical line inspector.
I was a little scared. I didn't know how I'd feel being back around the job and the equipment that I got hurt on. And I was a little embarrassed to come back. For one, I didn't follow the safety rules. If I had followed the safety rules at that time, we wouldn't be having this conversation, obviously. That's all I had to do was wear my gloves, and you're not talking about a big piece of equipment either that you have to, you know, struggle to put on and struggle to take off. You're talking about a pair of gloves. For the amount of time it took me to take my gloves off, it took less time to lose my arms.
Steve also gave safety lectures to the utility industry, and his story delivered a powerful message to fellow linemen.
Obviously, they realize what they're dealing with and kind of brings them closer together. I think as linemen, I think there's a certain amount of pride in the fact that they're linemen. They understand their job's hazardous, and when somebody gets hurt, it makes them all step back and think.
I give Steve a lot of credit to come through an accident like that, the amount of devastation that caused him and his family, and then to be able to come back and still work. I give him a lot of credit for that. I guess having somebody like Steve around, anybody that doesn't think that electric can hurt you, all you have to do is look.
Stephen Hayes is now happily married with 2 young children, and he wouldn't stand in the way of his kids becoming linemen.
It's a great job. It's very rewarding. You're at different locations, you're outside. So, as a career, I would recommend it. As long as you pay attention, as long as you take care of yourself, it's a great job.
All right, so you got zapped, and then they had to amputate the arms. So what happened? His bone marrow got fried. Externally, the muscles are fine. The bone marrow got fried. So why is the muscles are okay, but not the bone marrow? Any ideas? Any suggestions? What do you guys think? All right, so we got 2 questions for you. You get electricity out of a battery, so how do you put electricity into one? On top of that, this guy ended up losing his arms. He ended up getting shot. Bone marrow got fried, destroyed, got infected, so they had to amputate his arms in order to save his life, in essence. But his muscles, externally, if you're looking at it, everything looks fine. So why is it that the muscles were okay, but not the bone marrow? He said that he was lucky that the current didn't get to his brain. He was lucky that the current didn't get to his heart. How does he know that the current didn't get to his heart or brain? Well, underlying assumption is if it did, it would have been dead. Really? What does it take to kill someone? When magically end up losing both arms, and then stretch your arms, your heart is running in the middle, and then the current bypassed his heart, and magically bypassed his brain. Is it possible that the current can get to your heart and you still be able to survive? Is it possible that the current gets to your brain and you still be able to survive? So what does it take to kill someone? Okay, guys, this one is going to be slightly disturbing. All right, so this is not from TV, from the United States anyway. So we're going to see someone get shot. It's from the United States. All right, so a couple of things that I noticed over here. Number one, he doesn't even touch the wire. The answer to that question is no, you don't even need to touch the wire. The charges can arc through it. There's a large enough potential difference. The only thing he did, I don't think he meant to actually touch it. He thinks that he's acting safe. He's walking around, he raises his arm, and as soon as you do that, you will get zapped. That's what happened. Something that we discussed last week or the week before. Remember the spark? I said the distance matters. And spark is usually generated at a given distance. Once again, it is the same thing. Just get it into your heads. If there's a high power line nearby, just keep a safe distance. Keep a safe distance. You don't need to be touching it. If you're near enough, you will get zapped. That's the first thing. He gets zapped twice. By the time he's able to, he's just extremely close to it. That's what the problem is. So he gets zapped twice. He's falling down, and notice that the body started to smoke immediately. Okay, so what are you guys thinking, dead or alive? And most of you guys are thinking he's dead, right? Are you sure about that? And most of you guys are thinking, yeah, that's what it takes to kill someone. I got news for you guys. There's not much difference between what happened to this guy and what happened to the guy in the previous video. It's exactly the same thing. Yeah, you will lose consciousness, but are you dead? Not necessarily. So a couple of things that we did learn from this. Number one, you don't have to touch the wire in order to get shot. Just being near a high voltage line, power line usually is good enough for you.
This little light burns all day and all night. It burns on its own internet.
Your sound is a little messed up.
Firehouse.
Okay, so let's fix it. Or if we can fix it, let's fix it.
The video's okay. It's just your sound.
Okay. Let's watch it and then fix it, all right? Good background.
Since the pumper was pulled by a horse. Just gave enough light for the volunteer firefighters when they responded to the fire bell to come in, light their kerosene lanterns, get their equipment, and then go to the fire. That was 1901, when no one could expect the bulb would shine for a century. The Livermore bulb has been turned off only twice when it was moved to new station house. It has burned for 880,000 hours. The 4-watt bulb with early carbon filament was made by the Shelby Electric Company in Ohio. Look at it from below, and it seems to say it's on. Gary Drummond is an amateur local historian.
It's been one of those things in the community that's never been given. Oh, yeah, we've got a light bulb that's been burning for a long time down at the fire station.
This is the oldest burning bulb ever.
School children visit the light bulb. Either they, their parents, or grandparents were born when this light was first turned on. A visitor's book is filled with signatures from places like Japan and Ukraine. Today, the bulb hangs high out of the way, but it was not always treated with reverence. Fire Chief Gary Stewart says he comes to work every day hoping the bulb still works.
People would throw a Nerf ball or a Frisbee and it would occasionally swing on its cord. Some firefighters would come by and touch it to tap it for good luck. It was just the old bulb that was hanging around the house.
It isn't much to look at, and it doesn't cast much light, but it works.
And in a world that's just whirling with change, it's there, still, steady.
For those who ask why they can't make light bulbs like it today, the answer may lie in the fate of Shelby Electric, which went out of business. You can make light bulbs that last, but you won't last long making them. Brian Rooney, ABC News, Livermore, California.
So this light bulb has been around for over a century, right? So the question is why? And the company went out of business. Why do you suppose the company went out of business? I think I kind of know what you guys said. Did you guys hear that whistle?
Yes.
This computer is whistling. I don't get it. That's it. Okay, it started whistling last night. All right. I wonder if there's a virus. Anyway, so I may have to reboot the computer at some point. All right. Anyway, so this company obviously went out of business. So the question is why? And most of you guys are thinking it went out of business because obviously these guys are making light bulbs that could last forever, right? So if you got a light bulb that's going to last forever, that's the reason why the company goes out of business or something, because they're that good. Guys, that's not the reason why. Look at the light bulb. Okay, so hold on. We keep changing scenes. All right, so if you look at the light bulb, you will notice something about the light bulb, which is it's not generating a lot of light. Okay, look at the light bulb. Okay, company went out of business because the sole purpose of a light bulb is to generate light. I mean, you're not going to buy a light bulb because it's going to last over a century and you're not going to be able to see anything, right? Or much of anything. I'd much rather have a light bulb that lasts 30,000 hours, but I can at least see what's going on. So that's the reason why the company went out of business. So the question is, why is it that this light bulb is not generating enough light? The reason why it's not generating enough light is, you're looking at it, guys. Look at the filament. Number one, it's thick. It's thicker than the incandescent light bulbs that we have, the filament of the incandescent light bulb. We use tungsten today. Okay, so back then they were using carbon filaments. It was thicker, and notice that they made it really, really long. So why did they make it so much longer? And why is it so much thicker? And when you make it really long and make it really thick, why is that not generating enough light? So that's...
It's late. You've had a few drinks. There's no train expected.
All right, so let me ask you this question. How many of you guys ever been shocked by accident? Used to say electrocuted, and somebody corrected me. They say, hey, if you were electrocuted, you wouldn't be here. I said, what do you mean? I said, because electrocution is death by electricity. So coming from an art student, I have to check it, obviously. And sure enough, I went to one of my favorite sources, one and only Wikipedia, and sure enough, the person was right. So have you ever been shocked by electricity?
Yes.
Well, most of you guys have, right? Who has a really weird experience of being shocked? Does anybody have like some weird story? All right, let me give you one coming from an art student. Okay, so this story actually stands out. It was a farm boy. He must have been about 6 or 7, as far as he recalled. He was telling this story in class. So there was an electric fence around one of the farms that he was walking by, and then he would see sparks when it was raining from time to time. So he kind of wondered himself regarding, what would happen if I were to piss on it one day, right? So that's what he's thinking. So one day he's walking back home from school. Nature calls, and then he starts pissing. And I said, so what happened? He said, initially nothing. I was just fine. Everything was fine. And he could just see the sparks going up and down. And he didn't feel anything. And then he got this metallic taste in his mouth. And then the next thing, he felt this vibrations going up and down through his chest. And then then all of a sudden, he tries to stop himself from peeing. I asked him if he was able to. He said no. Everything was completely out of control. And then he got this burning sensation. He was not able to stop himself from pissing. And eventually, boom, obviously he ran out of urine. And then he falls down on the ground. And then it's a tremendous amount of pain. He looks down, and his little sausage is fried. So he rushes home. He's taken to a hospital. And then, he was given that burnt ointment. And that's the entirety of the story. I'm thinking, this is great. I said, can you just repeat this story and just capture yourself on video? I'm going to give you extra credit for it. He said, fine. Except somebody asked, so what'd you do with the ointment? He said, nothing. My mom's the one who applied it. So people stopped laughing. So he was embarrassed. And so that was the end of it. He decided not to do the project. Along the same lines, can you get shocked by pissing on something electrified? Better yet, can you get electrocuted by pissing on something electrified, like the third round? Okay, so this is the one that Mythbusters decided to test. All right, so those of you guys who've seen this story, Mythbusters is one of my favorites. Used to be, at least, when they were on.
Here's calling. What?
All right, so here's what they were going to come up with.
Could possibly go wrong?
Where are we? We're here at the Golden Gate Railway Museum in San Francisco, and we're testing the myth about peeing on the third rail.
Oh, this is the one guy found himself late at night in a train yard, peed on the third rail, the electrified rail, got electrocuted and died?
That's the one.
Some subway systems are powered by an electrified rail on the track. A steel paddle slides along the top of that third rail, arcing as it draws current. There's enough power in the New York subway to light the whole state of Vermont. Rob Lobenstein is the superintendent of that system. He's well aware of this myth.
My first day on the job, they give you all the safety tips and the warnings, and that's the very first thing they tell you not to do.
All right, so the Mythbusters, I love them for all the wrong reasons. The reason is because they're really good at putting together these little experiments. And for the most part, the conclusions are way off. And this is one of them. They will get this wrong, and they will get it wrong royally. And 2 people will die as a result. All right, so we were talking about step potential last week, so let's focus on that one.
Yeah, they're not as quick.
So the ground becomes electrified when there's a power line down. What would happen if you were to walk on this ground? All right, so we discussed this 2 weeks ago. What happens is you got the step tension, right? You need to keep your feet together. If there's any sort of separation distance between the contact points, there's going to be potential difference. So if there's a potential difference, the charges are going to be forced to go through your body, which means that you will get shocked. All right, so what's current? We're finally talking about electricity. The current is the electrical current. All right, so when you're dealing with current, now you're dealing with dynamic situations. So the charges, instead of being static and stationary, now they're moving, and they're moving in the same direction. Okay, normally in metals, the charges are free to move, and they're moving constantly. They jump from atom to atom, but they move at random directions. Okay, so as a result, there's no current inside metals. But if you have the charges moving in the same direction, now you end up getting current. That's the meaning of it.
An atom's nucleus has a positive charge. Electrons orbiting the nucleus have a negative charge. When electric current flows, electrons are torn from atoms and move freely.
Electricity is the flow of electrical charge, and most of the charge flows as electrons.
So the electrons moving in the same direction is what's considered current. So the charges moving in the same direction is what makes up current. The charges free to move are the electrons, so the electrons are moving in the same direction. All right, so the negative charges are moving in the same direction, so this is known as current. This is like a traffic flow. You're looking at a flow of electrons moving in the same direction. How do you get them to flow in the same direction? So you get them to flow in the same direction by generating a region of two opposite charges, two opposite charge regions. All right, so you got a negative charge region, you got a positive charge region. You got this wire, so you get the wire and then you stretch it between two opposite charge regions. So negative charge region is going to repel the negative charges in the forward direction. Positive charge region is going to pull the negative charges in the forward direction. So the electric field is going to be pulling from a positive charge region towards the negative charge region, while inducing a force on these negative charges. So these negative charges will accelerate in the opposite direction of the electric field. Okay, notice that this electric field is between two opposite charge regions separated through a distance of r, which means that this region is energized. The amount of energy within this region is known as voltage or potential. Remember that? Voltage difference or potential difference. All right, so if there's a voltage or potential difference, if you place free charge inside, what happens? The charges will become energized. Now these charges will have potential energy. So what happens to the potential energy of the charges? Because they're free to move, it's going to turn into kinetic energy. So larger the potential difference is, faster the charges are moving, the larger the current is, in essence. All right, so what drives current? Voltage or potential difference does. All right, so this is an energized region. This is electric field within the separation distance between two opposite charge regions. All right, so the energy is going to be stored within the electric field through the distance of r, which is known as voltage or potential. Free charges will become energized, so they will have potential energy. Because they're free to move, their potential energies will turn into kinetic energy, which means that it's going to turn into energy in motion. So instead of saying it that way, like, I have to put together almost 5 different sentences to explain a single concept. We will say the current is caused by voltage. That's it. So what is current? Current is the number of unit charges moving in the same direction. So capital N is the number, E represents unit charge, T is time. So number of unit charges moving in the same direction. So total number of charges moving in the same direction is known as current. So lowercase e is going to represent unit charge. In this case, electrons are the ones we're focusing on. Times is going to be in terms of seconds. Okay. So the symbol I is going to be our current. It's going to be expressed in terms of A. A means amps or amperes, or amperes if you're French, after a Frenchman. All right, so this is the same as net charge per second, net charge per time. Number of charges per second, net charge per second. Number of charges per time, net charge per time. That means current. All right, so number of charges, net charge, total charge. All right, so Q, net charge is coulombs, T is seconds. So coulombs per second is the same as ampere, or amps. It's the same thing. So it's the number of charges moving in the same direction at the same time within the same time period is known as current. So what drives current is the voltage differences. That's it. So current depends on the voltage difference. Larger the voltage potential, larger the voltage is, larger the potential is, larger the voltage difference is, larger the potential difference is. They all mean the same thing. The bigger the current is going to be. So the voltage represents the amount of energy stored within that region, between two opposite charge regions. More the energy is, the more the free charges will become energized, the faster that they will move. All right, so the current is proportional to voltage, meaning that the larger the voltage is, the faster the charges are moving, the bigger the current is. So what drives current is the voltage of this summary statement. So the current, one more time, is the number of charges moving in the same direction per second, per time. Okay, or number of charges moving across the wire. So what drives current is the voltage or potential. All right, so summary statement. So you got this wire or metal piece, got 3 electrons. You have to get the electrons to move in the same direction. So you create a region of 2 opposite charges, 2 opposite charge regions. And then obviously this wire is attached to both the negative charge region and a positive charge region. All right, so this is a negative terminal, this is a positive terminal. It's a negative charge region, positive charge region. There's going to be electric field from positive charge region towards the negative charge region. And the electrons will experience a force in the opposite direction of the electric field. They will accelerate in the opposite direction, which means that they will speed up. Stronger the electric field is, this positive charges are moving. So that's one way of looking at it. The second way of looking at it, all right, so you got a separation distance R between these 2 opposite charge regions. And there's an electric field. So the combination of the electric field and separation distance is going to tell you about the amount of energy stored. That's the voltage. And the free charges placed within this energized region will become energized, so they will have potential energy. And because they are free to move, the potential energy is going to turn into kinetic energy. So larger the voltage is, larger the potential energy is, larger the kinetic energy is, faster the charges are moving, the more the current is. That's what it means. So what drives current is, once again, the voltage difference or potential difference. All right, the thing is, we have to focus on, though, if you want to generate current using this, you get this wire. You got these 2 terminals, negatively charged terminal and positively charged terminal. As soon as you touch the wire to these terminals, what's going to happen is the negative charges will go from a negatively charged region to the positively charged region, and it's going to be done with. It's like lightning through a wire. Immediately, there's going to be discharge. Within a fraction of a second, the current is going to be done with. It's going to be over with. Unless somehow magically you can replenish the negative charges at the negatively charged region. All right, so how do we do that? How do we replenish electrons within the negatively charged region in order to keep the current going? How do we do that? Well, the way to do it is this. All right, so you need to keep the negative charge region negative and positive charge region positive for this to work. So you end up getting a continuous current. All right, so negative charge region is a negative charge metal. Positive charge region is a positive charge metal piece that we're looking at. So the whole idea is to keep replenishing negative charges within negative charge region. And in order to do that, what we do is we take these regions, both of them are metal, different metals, and immerse them inside an acid solution. Now, acid through chemical reactions will keep replenishing electrons within the negative charge region. So negative terminal is going to remain negatively charged. Is a positive terminal is going to remain positively charged. So which means that through an acid solution, we're able to maintain a constant potential difference between this region, these 2 terminals, which are separated through a distance r. There's going to be a constant electric field within this region. Separation distance is constant. So what the setup is known as a battery. I just created myself a battery. So what does the battery do? It maintains a constant voltage or potential difference between 2 opposite charge regions through chemical reactions. So as a result, what happens, the chemical energy will get converted into electrical energy in essence. All right, so once again, I'm describing something obvious. If you're looking at a battery, obviously you've got 2 terminals, and there's a separation distance between the terminals, right? And one terminal is getting positive charge, the other terminal is negatively charged. All right, so there's always going to be an electric field from a positive charge terminal towards the negative charge terminal. There's a separation distance that maintains a constant voltage or potential. And then how much voltage or potential it stores or maintains, usually on the battery. As you got a AAA battery, and you got 12-volt batteries, 6-volt batteries, whatever. All right, so it's just going to maintain that voltage difference. And if you attach a wire to it, and so all of a sudden what happens, the charge within the wire is going to become energized, so now they got potential energy. They're free to move, so their potential energies will turn into kinetic energy. So the motion of the charges is the current that you're looking at. All right, so that's the story of how you don't store current in a battery, you just store energy in a battery, in essence. All right, so you create 2 opposite charge regions, and you maintain the voltage and potential difference by placing these regions inside an acid solution. An acid through chemical reactions will keep replenishing electrons at the negative terminal. By the way, guys, when I say forever, I think that's almost correct. So this process will go on actually forever. The reason why the batteries end up dying at some point through happens because of corrosion. All right. As a result, you're not going to be able to replenish the electrons at the negative terminal forever. So that's what happens. In theory, you can do it forever, but in reality, obviously, life gets in the way.
Because different metals have different electrical properties.
First, we have 2 different kinds of metals here, zinc, and this would be copper. And they work as electrodes.
Okay, so zinc is going to be slightly negatively charged. The copper is going to be slightly positively charged, or vice versa. I don't remember which one it is.
And the lemon works as an electrolyte. So here's our little voltmeter.
All right, so the lemon is going to be our acid solution.
and see if we can get some sort of charge out of this lemon.
This is a classic school science experiment. The acidic lemon juice is stripping electrons off the copper, and they're flowing to the zinc, creating an electric current.
It looks like we're getting almost a volt out of just this lemon.
All right, so it creates a constant potential difference, 1 volt. All right, so you got a 6-volt battery. So larger the voltage is the faster the charges are moving, the more the current is. All right, so what drives current is the voltage or potential difference. So now that we have an understanding of it, here's your first simple electronic circuit. It looks like this. The symbol in the middle is a battery symbol. And negative terminal is going to be a short line. Positive terminal is going to be a longer line. The current represents the electrons moving from negative charge region towards the positive charge region. All right, so this is the way I will present it. In the books, they use the conventional terminology. If you have a book, textbook, whichever the textbook that you have, convention says the positive charges are flowing from positive to negative. Okay, so why is it that the physics says the negative charges are flowing from negative to positive and the convention says positive to negative? Because the convention started before physics got involved. All right, so we know today the charges are charges, these are particles. When they started to come up with these concepts of electricity, they were talking about electrical fluid. The electrical fluid would flow from a state of positive towards the state of deficiency, which is the negative. So state of surplus to this state of deficiency. All right, so this is the way Franklin used to describe it. So that became the convention. Okay. In the engineering courses, we use the convention. In the physics courses, we still use the conventional notations. In reality, the current moves from negative terminal to the positive terminal. Electrons are the ones who travel in that direction. All right, so if you have a book, if you're reading a book, I understand we're discussing the same thing. And the books use the conventional way of looking at it. I use the common sense way of looking at it. So that's how the conventional current.
Side man is out of the hospital tonight and urging dog owners to watch where they walk. This after his beloved pet was electrocuted on a sidewalk. And now city authorities are trying to get to the bottom of who's to blame. CBS 2's Sandra Torres is in Old Town for us. And Sandra, you talked with the dog owner this afternoon.
Eric, I did talk to the dog owner who was released from the hospital this morning. He suffered electrical burns to his leg and also a laceration in his hand. He is still trying to find out who needs to be held accountable. For Brian Malone, it's difficult to return to the place where his 6-year-old dog, LaDanian, died 2 days ago.
LaDanian was my first puppy ever. He was my treat to myself as a graduation from business school.
Today, there's just a small spot covered in cement. But as this picture shows, on Monday, there was an orange cone with electrical copper wiring attached to the fence. LaDanian got too close to it.
And next thing I know, LaDanian was shrieking and yelping and spasming like I've never heard. And looked like he lost control of his back legs. He eventually went down.
The mud died instantly, and Malone ended up getting hurt while trying to help him.
And in the process of me just trying to administer CPR, suffering burns up my leg from the voltage.
Now he's trying to find answers as to why the cone was there in the first place.
To have a residential fence be revealed to be electrically live 2 weeks ago, and then to not quarantine that off, and just to have some ground wire installed into the ground on the exterior of the fence, meaning on the sidewalk, that just doesn't make any sense.
And the city tells us it appears a private contractor was working on that fence, which is owned by the Marshfield Garden Apartments. And in a statement, they said that they are aware of this incident and that they are cooperating with the investigation. In the meantime, the dog owner is definitely considering looking into legal action. Live in Old Town, Sandra Torres, CBS 2 News.
Okay, so why did the dog die and not the owner?
Side man is out of the hospital.
The back leg was up my leg from the
copper wire.
I mean, this dog didn't have a chance.
I treat to myself as a graduate.
If you had a smart dog, though, it would have been fine.
And yelping.
If you had a chihuahua, that would have been 100% fine.
Like
and a cat would have been fine.
I've never heard.
And the reason why the dog ended up dying is because the dog is too big to live. That's a complete nonsensical statement in all appearance, but it requires a justification. This guy is fine. The dog didn't survive. So why is it that he's fine and the dog did not survive? Guys, it's the same. They're on the same ground. Once again, it's related to voltage and potential difference, guys. Remember, the voltage and potential difference depends on the separation distance between contact points. You got the hind legs and you got the front legs. Okay, the larger the separation distance is, the larger the voltage and potential difference is going to be, the more current is going to go through the body. Okay, this guy's feet are almost next to each other. Not much of a potential difference. He's on literally a live ground. This ground is live with electricity, and this poor dog doesn't know. He's just walking around because of the separation distance between the front legs and the hind legs is large enough. All of a sudden, there's a large enough current to actually go through his body and stop his heart. And then, of course, the animal didn't survive. In this case, his feet are almost next to each other, so separation distance is small enough. So this guy is perfectly safe. He doesn't even feel a thing. This dog is just whimpering. All right, so the larger the separation distance is, the larger the voltage difference is going to be, the larger the current going through the body. So the smaller the distance between contact points, the smaller the voltage difference is, the safer it becomes. All right, so that ground was electrified, and most people walking by, they were fine. They wouldn't even notice it. But if you have a dog, large dog, a big dog, and larger separation distances between the hind and the front legs, the bigger the potential difference is, the more the current goes through the body. Evidently, it was large enough to kill a dog. All right, so the current is the flow of charges. Just like traffic flow, it experiences resistance. So resistance is whatever resists the motion of the charges. Resistance is the effect of whatever resists the flow of the charges. So let's talk about resistance in general terms. So more the motion of the charges are impeded or resisted, the slower the charges will move, the smaller the current becomes. So what that means is there's going to be inverse relationship between current and resistance. So as more something impedes the motion of, more the motion of these charges are impeded, smaller the current becomes. And all of a sudden we got an interesting relationship. So R represents resistance. Resistance is going to be expressed in terms of the unit of omega. So this is a Greek unit. In English, it's ohms. There's a resistance symbol inside the circuit. All right, so you can have certain devices called resistors. So you can artificially induce resistance within the circuit in order to slow the charges down. So voltage is what drives current, and resistance is what diminishes current. What voltage is what drives current, what drives the charges to move in the same direction, and resistance is what slows down the motion of the charges in essence. So this is known as ohms because someone named Ohm, believe it or not, it's the real name, came up with this formula, and he came up with this formula just combining these two. So current, voltage is what drives current, resistance is what diminishes it. So if you want to turn this into an equation, what you need to do is you have to get rid of the proportionality sign. And that's exactly what Ohm did, and this is known as the Ohm's Law. Voltage is what drives current, resistance is what diminishes it, and that's it. And so this is a famous formula, and that could be visualized as part of a circuit just like that. So the current is moving in this direction. Voltage is what drives current, resistance is what's going to diminish it, and that's it. All right, so from a buck, conventional current, positive towards the negative, Ohm's Law. Voltage is what drives the current, and resistance is what's going to diminish it.
By a track. And finally, test your urine ability to conduct a charge. So the boys need a dummy that can answer nature's call. They'll start with a skeleton.
Okay, this is actually a nice one. Did it come with a body bag? Oh, wait.
Not the way they used to design these experiments. Except these guys are not engineers, they're not physicists, these are just special effects artists. So their lack of understanding of physics and engineering is going to create some problems here. It's going to cause two people their lives. Okay, so you end up watching this clip, which is about 5 minutes long. But the question is, how much did you really get out of it? Okay, so when you guys are watching something like that, you don't really do a lot of learning in essence. There's quite a bit happening here. It seems like these guys know what they're doing. In reality, we got a bunch of problems. One of the problems that they have is they calculated the electrical resistance of urine.
If you had a rather robust spring
They didn't calculate, they measured
of urine and you were able to spray it up on the ceiling in a, into a fluorescent lamp, you would probably receive the same effect as peeing on the third rail.
So peeing on the
famous
third rail.
electrical formula called Ohm's Law says the current equals voltage divided by resistance.
All right, so let's take a look at the amount of current that's going to go up the urine stream. Okay, so the third rail is going to give you 650 volts. It operates at 650 volts. They measured the electrical resistance of urine at 10,000 ohms. So the question is, what's the amount of current which is going to go up the urine stream? So that's when you end up using the Ohm's Law. The current is going to be directly proportional to voltage, inversely proportional to resistance. So put the numbers in. So it's going to give you 0.065 amps. And they will refer to this as 65 milliamps. Milli is 1,000 coming in. Okay, so you end up getting this. So the question is, would this be deadly enough to kill you? So I'll put a question mark next to it. And they will say, yeah, it could be deadly. If it gets to your heart, yes, it's large enough to give you a heart attack. That's what it means. Just because you're having a heart attack, does this mean that you will die? Not necessarily, no. Okay, so there are a bunch of assumptions here. This is the amount of current that's going up through the urine stream. Okay, just because it's going up through the urine stream, does this mean that that's the same amount of current that's going to get to your heart? Unless your heart is located right next to your balls, the answer to that question is no. Guys. It may feel like it when you're a teenager, but the heart is located deep within the body cavity. What do you have in between? What is it that you don't have in between? You literally have, you got fat, you got muscles, sometimes you have bones, you got crap, You got all sorts of stuff along the way. And everything that I mentioned is going to offer various degrees of resistance. So, which means that by the time the current gets to your heart, it's not going to be 65 milliamps. Would that still be large enough to kill? They'll take a look. Their experiment is completely going to fail.
18 and a half seconds for the system. Oh, whoopee. Spray. You had to fill it up. Why they're not working? So this thing. So the question took about now something's going to work. In this means there'll be a current.
Okay, so they got the numbers right.
And into a real.
Because of this.
A shock big enough to kill you. In this dry run, they'll try to pass that current through a tube of donated urine, through ballistics gel, and into a relay switch triggered at 65 million.
Okay, this relay switch is going to act like the heart within the body. And it's set to trigger at 65 million. The problem with that setup is by the time it gets to the heart, it's not going to be 65 million. So this experiment is not going to work. This experiment is designed to fail, and they're not going to know why it's failing. And they will mistakenly conclude that there's no way you could get electrocuted by pissing on an electrified fence like the third round.
And I think we should hear.
All right, so this setup is completely wrong. You cannot set this up to 65 milliamps. If it's 64 milliamps, it's not going to work. And it's going to it's going to create the impression that you're safe. You're not safe.
The thing click if it's going to work if I plug it in right now. There you go.
That's fantastic.
Yeah, they set it up. They set the trigger to 65. So anything over 65 is going to work. Anything under 65 milliamps, it's not going to work. And if the amount of current going up the urine stream is 65 milliamps, by the time it gets to heart, it's going to be way less. If you're lucky, it's going to be half that number. And it's still large enough to give you a heart attack. Get it up wrong. Okay, so we'll get back to that, and then we'll check to see how the experiment is going to keep failing. Okay, so we talked about resistance. Resistance is whatever resists the motion of these charges. So the question is, what caused resistance? Okay, so instead of the charges, notice that the electric field is from left to right. Acting on the negative charge will induce a force on these charges this is from right to left, so it's going to induce force on the charges from left to right. Meaning that the charges will accelerate uniformly from left to right, except here's what the charges do. They do a modern dance. They just zigzag around. They go this way, up, this way, that way, and then they end up zigzagging all over the place. You end up getting this drunkard's walk, the random walk. What's going on? Why is it that the physics just go haywire? The reason why it's happening is because of this, guys. These are the electrons, and you got this big balls all over the place making up the structure. All right, so I'm going to call these the red balls. What's causing resistance is the red balls in the way. Okay, so when I talk about red balls, don't go around saying that the resistance is caused by red balls. All right, if you do, don't mention my name. Okay, so I end up picking red for whatever reason. So the question is, what do these red balls signify? Red balls signify the atoms in the molecules making up the structure. Electrons are point particles, and these red balls are gigantic. Okay, these are huge. They are in the way. It's like a bit of a traffic pattern that you're looking at. The electrons are trying to move in this direction. These are like indestructible four tempos. You get in and there's no steering wheel. The only thing I have to do is just turn on the electric field. And as soon as I do that, these cars become energized. And they're going to start moving in the forward direction. And this is a highway. And I got all these random trailer trucks all over the place. And these trailer trucks are not moving at all. So these trailer trucks will become obstacles. So this four tempo is going to go up, hit one of these trailer trucks, and it's going to bounce at random directions. And it's going to gain energy. It's going to try to go through these trailer trucks. It's going to bounce. It's going to go at a random direction. So that's what's happening. All right, so the resistance is going to be caused by the atomic structure, otherwise known as resistivity. So you have this Greek letter rho, and that means resistivity. All right, so resistivity is going to be caused by the atomic structure or the molecular structure, making up the wire that you're looking at. Resistance is going to be directly related to the length of the wire. Once again, the traffic analogy works fine. If you have to drive a mile within this traffic versus 100 miles, 100 miles is going to be a lot more frustrating. So the longer you have to drive, the larger the resistance is going to be that you will experience. All right, resistance is going to be inversely proportional to the cross-sectional area, the thickness of the wire. All right, A is the cross-sectional area. That represents the thickness of the wire. Thicker the wire, smaller the resistance. Traffic analogy, single lane versus multi-lane. Single lane, one bad accident, entire traffic comes to a stop. Multi-lane, bad accident, slows down the traffic, but the traffic is going to keep on moving. And lastly, okay, so what else do we have? So resistivity, the atomic structure, the length is going to increase resistance. Thicker the wire, smaller the resistance. And the last thing that we have to deal with is the heat. All right, so temperature. Okay, so resistance, three contributing factors. You can turn this into a formula. Depends on the resistivity, that's the atomic structure. Depends on the length, L. It's going to be inversely proportional to the cross-sectional area, so that's your A. There we go. So that's the main formula. The last contributing factor is going to be the temperature. Larger the temperature is, larger the resistance is. Okay, so the question is how? Okay, so what's causing the temperature to rise up? What's causing the temperature to rise up is the heat. Okay, so the heat is going to be generated by the random vibrational and rotational motion of these molecules. Okay, that's known as heat. So which means the temperature is going to go up. As the temperature goes up, the resistance is going to go up. So how does heat increase resistance? Let's discuss that. All right. So electrons are, let's get back to the analogy of electrons being indestructible for tempos, and then these molecules, atoms and molecules being trailer trucks. Okay. Single trailer truck getting hit by a single 4 tempo is not going to make that much of a difference, guys. You're a trailer truck driver, and then next thing you know, you got hit. You will hear the crash. You will feel a little bit of a vibration, and that's it. And you will think to yourself, oh, we just got hit, and that's not a big concern. All right, so that's exactly what happens to the atoms and molecules, nothing much. Just getting struck by a single electron is not going to make that much of an effect. But imagine that you're just getting hit by billions upon billions upon billions upon 4 tempos at the same time. It's almost like being attacked by the Chinese military, guys. Regardless of which direction you look at, there's nothing. You cannot see the sky. All right, so that's what you're looking at. So eventually what's going to happen is that trailer truck is going to start to vibrate. It's going to sway this way, that way. The other one is doing the same thing. And so what happens to those passive gaps between these trailer trucks? The larger the gyrations, the vibrations are, the smaller the gaps between these, the trailer trucks will become. Likewise, the smaller the gaps between these molecules will become. And tougher it's going to become for these electrons to gain passage through these molecules. Right? It's going to be harder for them to go through these molecules, which means that the resistance is going to go up. All right, so the traffic analogy works fine, as long as you guys are taking physics at this level. Modern physics gets complicated, but this is good enough for our understanding of it. Okay, so larger the temperature is, larger the resistance is going to become, and the temperature goes up because of the increase of vibrational and rotational motion of the molecules. And larger the vibrations and rotations, the smaller the gaps between these molecules become. Okay, so that's what it means. So resistance goes up, temperature goes up, the resistance is going to go up. All right, so the temperature goes up, the resistance is going to go up. All right, so the temperature goes up, the resistance goes up because the resistivity goes up. The resistivity is related to the atomic makeup, the structure, right, of these atoms and molecules. All right, how it goes up is denoted by this formula. All right, so the increase of temperature is going to increase the resistivity from this value to that value. There's going to be an extra constant, which is known as the temperature coefficient of resistivity. But we're not going to put the emphasis on that mathematically. We don't worry too much about it, but just make sure that you understand the concept. All right, that's a little bit too much information that you won't be using in real life. Most of you guys are getting to health sciences, so let's stick with what matters to us at this point. All right, so let's get back to the terminology one more time. So resistivity is what inhibits the motion of these electrons. Okay, so what inhibits the motion is the atomic structure, the molecular structure. All right, so the more densely structured the metal is, obviously the larger the resistivity is, the larger the resistance is going to become. Length is going to matter. The longer the wire is, the larger the resistance is. Cross-sectional area, the thickness matters. The thicker the wire, the smaller the resistance. Also, the temperature is going to matter. Higher the temperature is, the larger the resistance is. Okay, so lower the temperature is, the smaller the resistance is.
Resistance to the progress of electrons. Just what is the nature of electrical resistance? Under the influence of an electric field, electrons move through a metal much as a marble falls through a viscous fluid. If it weren't for resistance, they would accelerate freely, like a falling body in a vacuum. But as it is, they move on the average at a constant speed. Resistivity is like viscosity. The more of it a material has, the slower a particle will move through it. But what slows the electrons down? In other words, in a conductor, what resists the flow of electricity? Inside a metal, electrons constantly move in all directions. Here, just a few of them are represented as dots. They orbit through the metal as if it were one giant molecule. This kind of flow encounters no resistance, nor does it create a net flow in one end and out the other. Under these conditions, the conductor is in electrostatic equilibrium. There's no electric field inside, no voltage difference from one end to the other. But if a battery makes an electric current flow, equilibrium is destroyed, and an electric field is created inside the conductor. Inside a perfect crystalline metal,
if a sample of it could be found, the mobile electrons would continuously accelerate, like a penny falling in a vacuum. But in the real world, crystals aren't perfect. They have defects and impurities, and their atoms vibrate with thermal energy. Electrons, accelerated by the force of the electric field, bounce off each imperfection, behaving somewhat like a ball in a pinball machine. All that bouncing, all that stopping and restarting, produces the resistance that prevents the electron flow from building up speed. So the electrons move at a constant average speed, creating a constant current under the influence of a constant force. As the electrons bounce off the imperfections, they set the atoms into larger vibrations. So the electrical energy of accelerated electrons turns into the heat energy of vibrating atoms.
Okay, so a couple of things to explain. You know, with the temperature, rising temperature, the resistance goes up. Okay, and the temperature goes up because of heat. Heat is going to be generated by the random vibrational and rotational motion of the molecules. And what set the molecules and atoms into vibration and rotational motion is the free electrons colliding. All right, so just to make the connection. The resistance is going to go up because the more the molecules vibrate, smaller the gaps between the molecules will become. The smaller the gaps, the larger the resistance. Okay, so that's what we got. Yeah. Let's get back to the circuitry. Every single device that you put into a circuit is going to offer resistance. You may have a TV, you may have a radio. Okay, so whatever it is that you plug into the circuit is going to add to the resistance of the circuit. So it just depends on how everything is connected or added to the circuit. If they are added in a serious sort of way, okay, so this is connected to this one, this is connected to that one, it's going to contribute to the overall resistance in a certain way. Or if you just connect every single appliance parallel to each other, as a result, overall resistance of the circuit is going to be different. So that's what we will discuss. So it's resistors connected in series. So you got 1, 2, 3 resistors are connected. In terms of resistors, they could be appliances or they could be resistors. Okay, so we got these little electronic circuit parts, which are known as resistors. So they artificially induce resistance in the circuit so that you can control the amount of current that you want to generate inside the circuit. All right. The best description that I'm going to give you, once again, is going to be based on a traffic flow. Okay, so imagine that you're going from work, you're going back home. So work is negative, home is going to be positive. And this is the direction that you will have to travel. Okay, except traffic speed limit, it's a sideways, or it's like 35 miles per hour, except there's this guy in front of you. This guy is texting and going at 20 miles per hour. Okay, so immediately you will feel the frustration because this guy is not getting up to the speed limit. And next thing you know, there's red lights. So that's going to increase the resistance. Once again, traffic is going to slow down further. And next thing you know, there's an accident. It's going to slow down further. All right, so which means that the fact of resistance of each and every single event is going to be additive. So it's just going to add up. And then your frustration is just going to go through the roof as a result. So when resistors are connected in series, just like that, overall resistance is going to go up. So you just add up the resistance values from each and every single event together. So the resistance is going to go up. The current is going to go up, which means that your traffic is going to slow down. Okay. So higher the resistance is, the smaller the current is, the slower the charge is. Right, so that's what happens when the resistors are connected in series. On the other hand, if they are connected in parallel, so we got these parallel resistors. Okay, everything is going to hook down to the same battery. Okay, once again, you're leaving work, you're trying to get home. This is the shortest path, the route that you can take, except boom, there's an accident. Okay, yeah, you can go through, but the traffic is not moving as fast. And plan B, you just go up to the next intersection. All right, so the traffic is moving fine, except there's a red light here. Okay, so you go, I could do better. So you're going to go up to the next intersection. Traffic is moving fine, except you got the guy who's texting. All right, traffic is going to move, but it's not moving at the speed that it could potentially because of one person. Okay, but the overall resistance that you will experience is going to be much less. Okay, so when resistors are connected in parallel, overall resistance that you will feel is going to be smaller. All right, so this is something that we will get to see next week. So you would be, if the resistors are connected in parallel, you add up the resistance values reciprocally. It's going to give you a reciprocal total. And then what happens is it's going to give you a much lower resistance. So smaller the resistance is, the faster the current is going to move, the larger the current is. All right, so that's what it is. All right, so let's talk about household circuitry. Household circuitry is a design using parallel or the circuits resistors in series. All right, so what I'm going to do is I'm going to just show you a design of a man cave. All right, I'm going to show you my favorite design of my man cave. If I had the money and time to do so, here's what I would do. All right. So I would have a room large enough, and I would make it extremely electronic friendly. Just go up to Menards or something when things are on sale and get myself about a mile of wiring, and then just get the wires and then just go beyond the drywall and then just wrap the wires from the ground all the way to the ceiling. Okay, so I would turn this room into a Faraday's cage in a weird sort of way. And then the wires, I would just wrap it all the way to the ceiling. And then next thing you know, because the entire place would be wired up, I could put sockets anywhere I want. So which means that I could turn this room into a lab, physics lab, if I wanted to. All right, so I would get my TV, flat screen TV would be located there, so I could watch my soccer over the weekends. I put the couch in front of it. The dog bed is going to be located right next to it. And then I would place a fire hydrant right here. Purpose of it is, you know, instead of taking the dog out because it's too cold, it could just piss over here, and then it would leak outside. Everything would be great. It's only in my imagination. And on top of that, you place the computer right here, the fridge right next to it. That's where the beer is. If you're a guy, ice cream. If you're a girl, everything is fine. And then what you need to do is you need to take these appliances and then you have to just hook them up into the circuitry. So the wires are already wrapped around the room. So what I need to do is just hook them up to the circuitry. So this wire, take the computer and then obviously plug it in. But now the current is going to go through the computer. TV is going to get plugged in. So the current is going to go through the TV. The fridge is plugged in. So it's going to go through the fridge. Right? All right. So when things are connected in series, just like that, this is the way it's going to look like. Except what happens, I leave. So as I'm leaving, I'm just going to turn off the TV. As soon as you turn off the TV, it's got to shut off the circuit. So which means that no current is going to be going through the computer, no current is going to be going through the fridge. So what happens to the beer? It's going to get warm. The ice cream is going to melt. No good. All right. So for this circuitry to work, all the appliances need to be on at all times. Okay. And that's a problem. So the problem is you should have current going through everything, and then it can cause an electrical fire. Hence the reason why it helps to have a fire hydrant inside the house. You're not going to be able to put out the electrical fire, but you may be able to protect what's in the house as a result. All right, so if you go with a cheaper option of just hooking everything up in series like that, if you turn off one of the appliances, it's going to shut down the circuit. It's not going to work. All right, so what's the best option? The best option is this one. Everything has to be set up parallel to each other. All these appliances should be hooked up parallel to each other. TV, you turn off the TV, it doesn't matter. It's still going to go through the fridge. It's still going to go through the computer. Got it? So all household appliances are connected in parallel to each other. Just remember that from this story. All right, so obviously this is going to prevent any sort of electrical wires. On top of that, you can turn on and off things at will without actually affecting the circuit. Okay, so let's talk about electrical power. And before we discuss electrical power, let's talk about power in general. Okay, so what's power? Okay, power is how fast the work is done, how fast the energy is transferred, or how fast the energy is converted. That's what it means. All right, so it's the energy per unit time, the work per unit time. So how fast the work is done, how fast the energy is converted, or how fast the energy is transferred. Speaking of power, there are two types of electrical power. All right, so there are two types of electrical power. When we talk about power, we talk about power being lost and power being generated. So you got power lost, power generated. So those are the two terms that we're going to be focusing on. Power is going to be lost through the resistors or appliances. Anything that resists the motion of these charges means that power loss, which means that it's going to slow down the motion of the electrons. Power being generated is going to happen within the battery. So which means that the energy is being produced. Power loss means that the energy is being lost, which means that it's going to be converted. Electrical energy being lost means that the electrical energy gets converted into something else. Power being generated is how fast the electrical energy is being generated. That's the meaning of it. Okay, so let's talk about power loss. So power is going to be lost through any appliance, which offers resistance. Okay, so when the power is lost, it's going to be lost in the form of heat as well as light. So power loss means how fast the electrical energy gets converted into heat and or light. That's what it means. So how fast the electrical energy gets converted. So what's happening is energy is simply being converted. It's not being destroyed. It's energy is being lost. Electrical energy is being lost, which means that the lost energy is going to appear in the form of heat and or light. That's what it means. All right, so the power being generated, the power is going to be generated at the battery. So the battery is an energy storage device. So it simply means how fast the chemical energy gets converted into the electrical energy. All right, so the power generated is how fast the chemical energy gets converted into electrical energy. All right, that's it. All right, so a couple of symbols that we will have to, three symbols, not a couple, it's three. We got three power equations. Okay, so the first one talks about the power being generated. All right, so if you're talking about power being generated by the battery, this is the one that we end up using, current times voltage. The second one is the power loss. Power is going to be lost through the resistor, or any sort of resistance is going to cause power being lost, for power to be lost, more like it. The third one is a summary statement. All right, so the power generated or lost, it doesn't matter. That could be expressed in terms of a summary statement. So you got the voltage, you got the resistance. All right, so the amount of power lost is more or less the same as the amount of power generated. This comes from the conservation of energy. It's just the side pole. Okay, so speaking of electrical power, power usually gets lost when there's an appliance that offers resistance. When the power is being lost, which means that the energy gets converted into heat and or light. So there's certain devices, such as a light bulb, whose job it is to generate light. So which means that it's going to offer a lot of resistance. So what you got to have is tungsten offers so much resistance that it heats up quickly and then it starts to glow, which means that the heat is going to turn into light. Okay, so larger the resistance is, more heat, larger resistance is, more light you're going to get out of it. So obviously tungsten is the one that we're looking at. Tungsten is going to offer a lot of resistance. So this is the resistivity of tungsten. So instead of using copper, you use tungsten because you end up, it's going to heat up faster. It's going to glow faster. It's going to emit more light. But immediately, if you look down below, right below tungsten, notice that you have iron. Iron has a resistance or resistivity. Almost, it's twice as large. It's twice larger than tungsten, almost, which means that this is going to heat up faster. It's going to glow a lot more, which means that it's capable of generating a lot more light than tungsten. Okay, guys, remember, iron is much more readily available. It's also cheaper. So why not use iron instead of tungsten? Any ideas? So instead of using tungsten, why not use iron? All right, going once, going twice. Okay, immediately, I'm hoping that you guys notice that larger the resistance, larger the resistivity, larger the resistance, more it's going to heat up, right? The problem with iron is it's got a melting point, which is fairly small. So using iron filament, you can generate light. It's going to be brighter. Except what happens to iron is it melts pretty fast. So it's not going to last more than 20 minutes. So that was the problem. Tungsten has a much higher melting point, so it can last up to 25 to 30,000 hours. So that's the reason why we use tungsten.
These balls have a life expectancy of 25,000 hours. I'm on a roll tonight, dear.
A light bulb lights because its filament offers some resistance to the flow of electrons.
Okay, that looks better.
As the electrons try to crowd through a hair-thin tungsten wire, the energy spent overcoming resistance turns into heat.
A material that's resistive is one that requires some kind of work to push the charge across. That means you're giving up energy that turns into heat and will heat that element up.
And here, heat means light. The filament reaches a temperature of about 4,500 degrees Fahrenheit.
All right, so speaking of light bulbs. Okay, so the power loss is going to appear in the form of light, right? Larger the resistance is, more power is going to be lost, the brighter it's going to be. Just remember that. Now, the filaments, a couple of things about the filaments. Number one, they offer a lot of resistance because of the simple reason is that they have extremely large resistivity. All right, so tungsten has an extremely large resistivity. The larger the resistivity is, the larger the resistance is, the more light you end up getting out of it. So that's the way it works out. The other thing that they do is they make it really thin. All right, so thinner it is, the larger the resistance is, the brighter it's going to be. All right, so that's how it is done. Okay, so let's get back to, let me just take a look at something. All right, before we get back to it. So in terms of the light bulbs. Now, think back to the beginning of the lecture. Remember the light bulb lasting over a century? I think it's still working properly. Okay, it's had a few problems. The number one problem that he had was, I'm going to use this one. They were using a carbon filament. Okay, so they were still looking for something better than carbon. Obviously, eventually they settled on tungsten, but at the time they weren't using tungsten. The carbon was the best that they had. Now, this didn't have a large resistivity, so it wasn't generating enough light to begin with. So what do you do? So they decided to make it really long. So what happens when you make it really long? When you make it long, it increases the resistance, all right? And then as a result, it was able to generate a certain amount of light. And with carbon, once again, you can make it thin, but you cannot make it extremely thin. So they try to make it as thin as possible, but there's a limit to it, obviously, with carbon. So that's the reason why once they reach the limit, they can do anything else. With that, they were able to increase the resistance to a certain degree. And with that amount of resistance, that was the best amount of light that they were able to generate, and it wasn't good enough, basically. All right? Eventually, the company went out of business because they weren't good at making light bulbs that actually generated well enough light. All right? So that became a problem. Okay, so let's do a quick review. Okay, so what I want you guys to do is you have the handout already, so just go find the handout. And then we'll do a review from the handout. So you got my lecture handout. So what you guys are looking at is the battery. So what is a battery? Battery is an energy storage device. Energy is going to be stored in the form of voltage. The voltage depends on the separation distance between these terminals, right? So you got these terminals. And there's electric field between these two terminals. So the strength of the electric field and separation distance is your voltage that you get from a battery. So you have to, batteries are designed to keep a steady voltage difference, and this happens because they're able to replenish electrons at the negative terminals through acid solutions. Okay, so you end up getting this steady potential difference or voltage difference. Okay, so if you get a wire, piece of wire, and if you attach the wire to the terminals, what's happening is it's going to set up an electric field within the wire. Okay, and then you got these free electrons. So free electrons will accelerate in the opposite direction of the electric field. That's one way of looking at it. The second way of looking at it is you got these free electrons, right? This region is energized. So what happens is the electrons become energized. So they have the potential energy, because they are free to move, that potential energy turns into kinetic energy. All right, so the kinetic energy of these charges, the motion of these charges is known as current. So what drives current is the voltage or potential difference. All right, so traditional way of following the current, the positive charges move from a surplus state to a deficient state. They go from positive to negative. The reality is the negative charges are moving from a negative terminal to the positive terminal. So the larger the voltage is, the larger the current is going to be. So what is current? Current is the number of charges moving in the same direction, or net charge per second, or number of charges going across this cross-sectional area per second. And these are all the same definitions. Okay, so a couple of things that I didn't emphasize. Let's talk about the junction rule. Okay, so notice that this is part of a circuit. There's a junction right here. It's incoming current. Part of the current is going to go this way. Part of the current is going to go that way. If you're looking at any single junction, and let's take a look at it, guys. The junction is located right here. All right, so here's the incoming current. All right, so IO is the original current. So the current is going to split. Part of it is going to go this way, and the other part is going to go that way. So according to the junction rule, the sum of all currents at the junction is going to add up to 0. Okay, which means that the amount of current that goes in and the amount of current that's going to come out will be equal to each other. All right, so here's the incoming current. If it's going in, that's taken to be positive. If it's leaving the junction, it's going to be negative. All right, and this happens because the net charge is going to be conserved. What that means is the charges cannot be created or destroyed. In essence, that's the same statement. All right, so we got our junction rule. Didn't need to kill it, but let's go forward. All right, so that is our junction rule. Okay, so move forward. Okay, so we discussed that. So the charges will have potential energy inside the wire. They are free to move, so it's going to turn into kinetic energy. Mechanical energy is going to be constant because electrostatic force is a conservative force. The rest of it is not that important. So, okay, what else do we have? We talked about the Ohm's law. The current is going to be directly proportional to voltage. It's going to be inversely proportional to resistance. The resistance is going to be expressed in terms of ohms. Resistance is whatever resistant motion of these charges. So here's the basic circuit. Ohm's law is expressed in terms of the voltage difference. So isolate V. Okay, and that's it. Okay, so the resistance is going to be caused by the atomic structure. So this is known as resistivity. Resistance is going to increase with length. Okay, it's going to be inversely proportional to the thickness of the wire, and resistance is going to be directly proportional to temperature. The temperature increases because of the vibration motion of the atoms and molecules, and the atoms and molecules are vibrating because the electrons are colliding with them. Okay, so what else do we have? So that's pretty much it. So that's not that important for you guys. And then the last thing we talked about is the power is going to be lost through anything that resists the motion of the charges. The power is going to be supplied and generated by the battery. Power lost is how fast the electrical energy gets converted to heat and whole light, and power generated is related to how fast the chemical energy gets converted into electrical energy. All right, so we discussed the formulas. Okay, so what else have we done? All right, now let's focus on electrocutions.
The safety of knocking tires can cause extreme action in the quest for excitement.
All right, so the question is, can you get electrified?
In In fact, there are no recorded cases of O'Malley or anyone else dying like this in the New York subway.
Watching breakup in every stream that we photographed, just doesn't look like you can make a solid connection. I'd say that's a myth busted. Not that I'd be peeing on the third rail anytime soon.
The electric release is like a human heart. If it's triggered, he's a dead man.
Let's make the set hot. Hot set. 3, 2, 1.
Okay, so the main reason it's not working is because they set the trigger too high. Relay trigger was set to 65 milliamps. Resistance matters. In terms of resistance, the material between the urine stream and the heart is going to matter. Obviously, there's a lot of material that's going to offer a lot of resistance. So by the time the current gets to the heart, it's not going to be 65 milliamps. So the relay was never going to get triggered. Everything else that they're doing, they want to make the ground wet, makes no difference. It's not going to make any difference. The main distance, the proximity is a reason, and also there's a lot of resistant material in between. So that's not going to happen in real life. Only way they were able to get it to work, though, they had the current go through the arms and all that stuff, and then that reduced the proximity. There was a large enough current getting to the relay. Eventually, it worked out. They put the emphasis on the urine stream. Urine stream has nothing to do with it. They said that the urine was just breaking apart. Guys, it's reality. If there's a large enough voltage difference, the current is just going to arc through the droplets. It makes no difference. It makes no difference that the urine stream is going to break apart. Okay, that emphasis is not that important. Remember the guy on top of the train ended up getting shocked? And I'm not sure if he survived or if he died, obviously, but he didn't even touch the power line. He was just close enough to it, and then he raised his arm. And obviously, the distance matters in terms of lightning, in terms of generating spark. So the voltage potential difference was large enough for the charge to jump through the gap. So it's the same. 640 volts is, if you're pissing on it, you will get electrocuted. In fact, two people, one from Chicago, the other one from New York City, Brooklyn, ended up pissing on the third rail, and they didn't survive.
It seems that we have to revisit the story peeing on the third rail.
All right, so when they make a mistake like that, they hear from people. Right? They hear from people who get shocked by pissing on something electrified. They hear people like myself, and then they hear that they got it wrong. Their conclusion was way off. They concluded that it would be next to impossible to get shocked.
It seems that
not only would you get shocked, but also you could get killed. Nice thing about them, and when they make a mistake, or at least they sometimes go back and they repeat the experiment. And this is one of those experiments that they will repeat and still get it wrong.
We have to revisit the story peeing on the third rail. We thought we did a great job with it. We tested it. We thought we busted the myth.
In the original test, the Mythbusters replicated the electrified third rail, often used to power subways.
How's the P-aim look?
P-aim looks pretty good to me.
With our test subject O'Malley's stoic assistance, they found in normal circumstances, there's no way a fatal current can jump up a urine stream.
Not a thing.
The reason? A few inches after release, the urine stream breaks up. It needs to be solid to carry the jolt.
A lot of people are sending us emails saying that, well, I beat on an electric fence on the farm and I got a shock.
Okay.
Jamie and Adam have called in builder Tori Felici from their workshop to help put this one together.
I basically think we're still going to be right about the reasons you can't get electrified peeing on the third rail, but we've got to build a rig that simulates an electric fence. Okay. So I think we ought to have half the farm fence with a single wire and half, like, maybe a 2-foot square section of chain link fence as well. You should probably be on the city side. Farm boy, city boy. Yeah, I think I would.
To recreate those viewers' adventures down on the farm, the Mythbusters need a fence. It'll be half chain link and half single wire, and they'll hook it up to an electric fence energizer. Then they'll do what comes naturally.
It just doesn't seem right.
To prevent killing livestock, the energizer delivers a low current in very short pulses.
It's not going to continue to zap you. It's only going to be in a pulse. So, it's just enough to give you a serious jolt.
I'm not looking forward to it, but I'm ready to try the experiment. Are you?
I'm not doing it.
Can I point out that I've already been painted with gold paint and had an anal probe today?
You're doing a wonderful job.
It seems an electric jolt to the genitals is beyond the limits of myth-busting solidarity. It's just Adam, the fence, and his now close friends, the paramedics, with their heart monitor, just in case.
I just, like to get a confirmation of my assumption that an extremely low amperage high voltage hit is not going to perhaps cause my to malfunction from here on in.
Hey, Adam.
Yeah.
You're not pea-shy or anything.
I'm not pea-shy. No. I believe I've proved that I'm not shy in any way.
Time to show your stuff.
Why don't you hold my hand while I pee, and maybe you'll get a shot. Oh, okay, we're going to try it in here.
The voltage is higher than in the original third rail experiment. And even more importantly, this time, Adam's much closer. Just 3 inches from the wire. There should be a solid stream.
I got to work one up. Hold on.
Is there a problem there?
I may be a little pea-shy. There's like 50 people in the room. All right, here we go. Are you ready? There we go. I got a shot. It was nothing. I got it. You did?
Yeah.
Oh, right there.
Beautiful. We proved that I got a shock. Right there. It was nothing.
Our initial results still hold. You know, the myth is busted.
We never said it was impossible to get shocked. We just said that even though urine conducts electricity, you have to be ridiculously close to the source for that to conduct. And we proved that again. And we still yet to find a single case confirmed of someone dying from being electrocuted by peeing on an electrified rail.
I was being cautious, as everybody in our viewing audience should also be.
This one's definitely busted. Let's move on.
Okay.
Okay, so they busted it despite the fact that two people more than likely believing in the show and not realizing that this is just commercial TV. End up losing their lives over it. Guys, what matters is the potential difference. If the potential difference is large enough, the current is going to be large enough to kill. So that's what happens. So the next question is, what does it take to kill someone? All right, so the large enough current, what do we mean by the large enough current? Okay, before we do that, now that they busted the myth, okay, let's watch some people getting shocked by pissing on something electrified. Both of them end up going down at the same time. Okay, so my favorite is this one. Yeah, the one before this. He knows he's gonna get zapped. He's gonna do it anyway. I think this. He knows he's gonna get zapped. He's gonna do it anyway because I think this is more of a dare. Right.
What would happen if you...
This guy's gonna do a far better job than Mythbusters did.
...on an electric fence? When a man's got to go, a man's got to go. But what would happen if you peed on an electric fence? Now, this should be a really easy question to answer. You find an electric fence and you pee on it. The trouble is finding someone brave enough or stupid enough to do it. So before I drop my pants and answer nature's call, I think a little bit of experimentation is in order. Now, we have attempted to recreate the famous Brussels monument mannequin pee. It's not a scratch on the original, but it should serve our purposes nicely. Our chap here is currently just recycling water. So what we're going to do is add some salt to recreate as closely as possible the wastewater our bodies produce. Urine is around 95% water. The remainder is mostly salt and urea, and it's these elements that carry the charge. Now, the first thing to do is to switch on the electric fence. Okay, that's on now. Now we're going to measure the voltage coming off this machine. If I, whoa, you can see that. Now, from top to bottom on this screen, it's about 400 volts. And whenever I get one of these big peaks, which you see happening now, there's one, it's blowing it way off the screen. But that's no great surprise, because we know this is 6,000 volts. So what I'm going to do now is attach my probe to the beginning of the stream, like this. And what I'm looking for is to see if I get any sort of blip at all. Because even the smallest blip means I'm getting at least 100 volts. And 100 volts is the limit I've set myself. More than that, and there's just no way I'm going to do this. So, here goes. I'm going to move the fence into the stream now. Like that. Let's have a look. Let's see what we're getting. I'm sure I don't have to tell you that I'm very keen to see some activity on the oscilloscope. A shock of less than 100 volts would still be unpleasant, and I will be a much happier man when I see some big blips. We're not getting as much through. It's definitely reduced. Whoa, there was a big blip there. Whoa, that was really big, but that was at least 150 volts. That's a sight for sore eyes. There was another one. Now I'm getting blips there that are almost the full screen, so that means there's probably almost 400 volts at the beginning of the stream. And that is 300 volts more than the limit I set myself. That's a big relief. The charge is definitely travelling up the stream, and at the source there could be even more than 400 volts. Right, that's all the evidence I need. Now, while I can't tell you exactly what would happen if you peed on an electric fence, what I can tell you from this experiment is that if you did, it would hurt like...
All right, so anyway, the larger the voltage difference is, the larger the current is.
Southwest suburb.
So the question is, what kills and what doesn't?
Say an electrocution yesterday started with an innocent water balloon fight. Alsip police say 12-year-old Sean Thompson was standing in a puddle of water. He received a fatal shock when he grabbed an electric garage door as it was closing. The victim's 11-year-old friend, Jared Gallivan, tried to pull Thompson away, but he was injured as well. Authorities say the garage door opener may not have been properly grounded.
Okay, so what's the meaning of something being properly grounded or not being properly grounded? Obviously, it's not properly grounded. The current can go through your body and it can kill you. The sort of stuff that needs to be properly grounded before we talk about the grounding is anything which has a metal casing on it. All right, because if there's current, obviously, the current is going to reside outside of the metal casing. If you come in contact with it, the current has no choice but to go through your body. Okay, so that's what creates the problem. So if it's not properly grounded, there's a loose wire touching the inside of the metal, the current is going to be outside. So you come in contact with it, the current has to go to the ground, it's going to go to the ground through your body. So you will become part of that circuit. Okay, so what is the problem with that one? All right, so your body's going to offer a little bit of resistance. Okay, we're good conductors, but we're not like metal. We offer a lot of resistance. Okay, so what's happening is, this is the dryer. It's metal, it offers a certain amount of resistance. The body is going to offer a lot more resistance. Okay, if these look like the flames from hell, it's probably going to feel like it. Yeah. So, which means that when you come in contact with it, the current doesn't have a choice but to go through your body, and the body's going to offer some resistance. Okay, the amount of resistance offered by the body.
The path that leaking electrons follows depends.
The current you coming out of the socket is not so large that you're going to glow.
On the material they flow through.
The human body certainly will conduct current, but not a lot. Not like a piece of copper.
But it's going to conduct current. So the amount of current coming out of the socket is usually not that high.
It's no big deal.
How are we going to do it?
All right, fine, I'll do it.
It's depending upon the body's resistance. It could be as high as like 12 milliamps.
Oh, Mama. Are you okay? I'm going to lose that name.
They keep the voltage low enough just in case, because they don't want you to die, if possible. This is phenomenal acting. Seinfeld, obviously, it's a comedy show. Used to be. Michael Richards, playing Kramer. All right, so he's got the paperclip. He's wetting it as if it's going to make a difference. It's a good conductor to begin with. All right, so as soon as he makes contact with the current, his body's going to become stiffened, and this is phenomenal acting. All right. So your body, you feel paralyzed in essence because it's alternating current. It just hits your body, it paralyzes the muscles, and then there's a circuit breaker. It just kicks in, and then the current is out. In most modern buildings, this is what should happen. All right. Now, the amount of current going through the body, if the resistance of the skin is 10,000 ohms, which is not, it would be about 12 milliamps of current. So would that be large enough? Remember, we were discussing 65 milliamps of current. That's the amount of current going up the urine stream. Would that be large enough to kill you if it got to the heart? About 12 milliamps of current. Would that be large enough to kill you? In reality, 65 milliamps or 12 milliamps of current, if it were to get to the heart, it would be large enough to give you a heart attack. All right, so 12 milliamps, 65 milliamps, it would be large enough to give you a heart attack. If that's the amount of current that gets to the heart. Now, if somebody's having a heart attack, the thing to do is to stop the heart. In order to stop the heart, you have to stop the heart momentarily. Something that we discussed before, we just shock the heart just briefly, stop it, it resets itself because it's an electrical loop. You need to pump in about an amp of current. At the very least, you have to pump in about an amp of current to stop the heart, and then it resets itself. So if somebody's having a heart attack, you kind of shock their heart. So 65 milliamps of current is going to actually give you a heart attack. And if somebody's having a heart attack, you have to stop their heart and reset the heart by pumping about an amp of current into the heart. All right, so 65 milliamps of current or 12 milliamps of current can be deadly. Here's the problem, though. Current has to kind of build up inside the body. When you come in contact with the outlet, and then somehow if you touch the exposed wire with your palm, if you just grab it, if you're not able to let go, what happens is initially it doesn't feel like anything, believe it or not, guys. You feel these vibrations going up and down your arm, and then you try to let go, you're not going to be able to let go. The next thing you know, it starts to travel inward into the body cavity, gets to the lungs, so you're going to have a hard time breathing. Eventually, when it gets to the heart, because the heart is an electrical organ, it just messes up the natural rhythm of the heart. Eventually, it gives you a heart attack. So that's what happens. So it doesn't necessarily happen right away. It takes a while before actually you can have a heart attack. All right, so it's not going to be instantaneous. All right, so what do you have to do in order to avoid that? Anything that has this kind of a metal casing has to come with a 3-prong plug. It needs to have a 3rd prong. What does the 3rd prong do for you? Look, what happens is the 3rd prong is the grounding in essence. You got a wire which is going to be touching the inside of the metal, and then it is attached to the 3rd prong. The 3rd prong, it takes you to the ground. So what happens is when you come in contact with this, the current is going to have a choice. Either it's going to go through your body to the ground, or it's going to go through to the ground through the 3rd prong. All right, so which one will it prefer? Let's take a look at it. All right, so here's what the 3rd prong does. It's a grounding wire, all right, which offers a little bit of resistance because it's metal. Okay, a wire is made up of metal. Your body offers a lot more resistance than the wire does. And notice that the grounding wire becomes circuit that becomes parallel to your body. All right, so given a choice, the current is going to, most of the current will take the path of least resistance. So the wire offers a lot more resistance than your body does, which means that a lot of the charges are going to be traveling through the wire to the ground instead of going through your body. Okay, some of the current is going to go through your body, but not much. You're not going to feel it. All right, so that's the reason why any appliance with metal casing has to be grounded. So any appliance with metal casing, let me repeat, any appliance with metal casing needs to be grounded. Or else, if there's a loose wire touching the metal, everything is going to become electrified. If you come in contact with it, if it's not grounded, this current has no place to go but through your body to the ground. And then, just like that kid ended up getting killed, because the garage opener was not properly grounded. As a result, it just went to the ground through his body and then killed him. All right, so the third prong is a grounding prong in essence. So it's attached to a grounding wire. And the way it works is the grounding wire becomes parallel to the main circuit. It becomes parallel to your body in essence. And because your body offers a lot more resistance than the grounding wire, it actually makes you safe in that sense. So not much current is going to go through your body. All right, so we talked about accidental electrocutions. Now let's talk about the intentional electrocutions. We're talking about the electric chair.
They normally...
The United States is the only country that has the electric chair. It was invented in the United States. It was a primary mode of execution for a long time.
See the arm suddenly gripping the chair. This is due to the spasm. They often see steam coming out of their mouths or their ears and occasionally flames because the heat of the electrocution melts the fat in their faces and it sometimes vaporizes and it sometimes catches fire.
All right, so the idea behind the electric chair is get to the heart, stop it, and fry it. Okay, so what does it take to actually stop the heart? It takes 1 amp of current. If somebody's having a heart attack, you shock the heart, fraction of a second, about 1,000th of a second. The whole idea is to stop and reset. All right, so instead of stopping that for a fraction of a second, why not just stop it for up to a second, about 2 seconds, 3 seconds, long enough to fry the heart? Okay, so that's the whole idea. All right, so regarding the executions, obviously it's done in the name of justice, whatever that means. And they provided that the person who's being executed can be executed without suffering any undue pain or whatever. All right, so as long as you can execute someone without causing any undue pain or suffering, obviously that's considered a viable method of execution. So the question is, can you get to the heart with large enough current within a fraction of a second, and then be able to stop the heart and fry it without causing any undue pain or suffering? Okay, if the answer to that question is yes, then it's a viable method of execution. If the answer is no, obviously it's not a viable method of execution. All right, so that's what we're going to be studying right now. We're going to be focusing on the physics. All right, this is nothing about the morality of executions. I mean, every single state has its own stand on it, obviously. So we're not going to be talking about that. We're just going to talk about the physics of it in essence. So can you get to the heart within a fraction of a second, 100% of the time, and be able to stop it and fry it without causing any undue pain or suffering? Okay, so we will investigate. So in order to investigate, what we will do is we're going to take a look at the first execution in history. Okay, so you're not going to see anything outlandishly bad because it's going to be from the History Channel.
Electricity is an extremely humiliating way of killing people. It's humiliating partly because the person vomits and drools. Their tissues swell up like a Michelin man and may burst. They pass water and defecate, and usually there's a horrible smell.
What's the smell?
Well, the smell is actually boiling urine, boiling feces, and burning skin. A pretty unpleasant smell altogether.
Okay, so a couple of things. Number one, they will pump about 20 amps of current into the body. It's exactly the same as the capacitor. Remember, defibrillator. 20 amps of current into the body cavity, while hoping that at least an amp of current is going to reach the heart and stop it and fry it. So they will keep it long enough. That's the whole idea behind the initial execution. This guy's a neurologist. He's a medical doctor. So he's just talking about the sort of stuff that you would see. I'm not sure if he's has a personal experience, but he's talking as if he does. All right, so the fat obviously is going to resist right under the skin. So what do you expect? The fat is going to melt. It's going to bubble. If you see anything, you will see the fat bubbling under the skin. On top of that, the body offers resistance. So what that means is the body's going to heat up. The body's going to heat up quite a bit. And so the skin is going to start to burn. You will be able to smell it. So it's AC current, alternating current. So which means that it's going to paralyze the muscles. And then it's going to paralyze the internal organs. So whatever you may have in your body is going to leak out and it's going to boil. It's literally going to shock the crap out of it. All right, so it's not going to be a pleasant experience to witness. Witnessing something like this is not going to be pleasant. Okay, so I'll give him that much. My question is, can you get to the heart within a fraction of a second and be able to stop it and fry it without causing any undue pain or suffering? So let's look at it from the perspective of a person who's being executed. So the first execution, believe it or not, took place in Buffalo, New York. And they got a volunteer for it. And when I say they got a volunteer for it, it wasn't like they went out to the street and said, hey, we're just going to do this, would you volunteer for it? No, they talked to a person who was on the death row, and then they told them the idea. They said, hey, this is a viable method of execution, and we can actually kill you without causing any undue pain or suffering. They explained it to him, and he bought into the idea. In a sense, he did volunteer for it. All right, so here's a reenactment of this thing. All right, so immediately I noticed a problem. Number one, the amperage is too low in terms of amps. It needs to be around 20 amps. This is the first execution. This is trial and error at this point. Obviously, they got a volunteer. They think they're going to be able to pull it out. So this is about 6 to 8 amps that I'm looking at. Ignoring that, I see a big problem. The problem is this person is grunting. Okay, which means that the person is in pain, which means that the execution is not taking place the way it was fashioned. Yeah. The person is grunting. That means that number one, the lungs are working. If the lungs are working, which means that the current is not getting to the lungs, it's not getting to the heart. 6 amps of current is a tremendous amount of current, so it's not going into the body cavity. Now we got problems. If it's not going to that body cavity, where is it going? It's right under the skin, inside the bone marrow, for God's sake. All right, this guy is actually feeling it under the circumstances. He wants to yell and scream, but he can't because the muscles are paralyzed. So the only thing that he could do is grunt and grunt and grunt. All right, so at some point they stopped the execution because he stopped grunting. More than likely he passed out.
Minutes after Kemmler died, Dr. Southwick, who was one of the men instrumental in the invention of the electric chair, said, "Today we live in a higher civilization." He was pleased. He said, "I am one of the happiest men in the state of New York today." And over again, there was talk of increasing civilization, a higher civilization, and the word progress appeared repeatedly in the arguments for the electric chair.
The warden said, "Kemmler is dead." And then somebody in the crowd yelled, "He's still breathing." And Spitzka screamed, "Get electricity back on." This time they left it on for 4 minutes, until Kemmler's body finally caught fire. And it was at that point that they gave the signal to shut off the electricity. And through the whole room, they were in the same room as he was in, and they were probably 10 to 15 feet away at the most. The whole room was filled with smoke and the smell of burning flesh. And it was just a horrible scene.
They didn't have the generator tied down properly, so when they were running the current through Kemmler, they were running the generator with some belts. The belts were coming off of the generator, and the person had to be up there kind of push the belts back on as they're getting the electricity into Kemmler's body.
Well, the Attorney General actually fainted, ran out of the room holding his stomach, and then he fainted. Most of the other witnesses were terribly shaken up by this, because they had, I think, like Kemmler believed, that this was going to be a quick and painless death.
It is usually believed, because they want to believe, that death is instantaneous. It simply isn't true. The fact is that they die due to asphyxia, which takes from tens of seconds to minutes. And that is because the electric current stops them breathing while they can still feel.
Okay, so a couple of things.
They want to believe that death...
He had, I think, like Kemmler,
to believe that death...
Okay, so this guy's a medical doctor. He's a neurologist.
It simply isn't true. The fact is that they die due to asphyxia, which takes from tens of seconds to minutes. And that is because the electric current stops them breathing while they can still feel. They die to...
All right, so he's a medical doctor, neurologist. I'm a physicist, so I'm just going to disagree with him 100% on that one. If the current gets to the lungs, it gets to the heart at the same time. If it can paralyze the lungs, it's going to paralyze the heart at the same time. All right, so that's it. Can you get to the heart within a fraction of a second and stop it and fry it within a few seconds? If the answer to that question is yes, it's a viable method of execution. Okay, but the question is, can you get to the heart within a fraction of a second and be able to stop it and fry it without causing any undue pain or suffering? All right, if it gets to the lungs, it gets to the heart at the same time. While the person feels something for a while, blah, 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 that's besides the point, because normally, regardless of what the method of execution is, guys, just because you stop somebody's heart does not mean that they lose consciousness immediately. How do we know that? I know that stuff because I get my information from Wikipedia, and Wikipedia gets its information from experts. People conduct animal experiments. You stop the heart, the brain is still active after like 20 seconds or something. All right, whether it's decapitation or broken neck or whatever, it makes no difference. There's still got to be a lingering awareness that lasts almost like 20 seconds. My question is, can you literally get to the heart within a fraction of a second and stop it? The answer to that question is no. Oh my God, no. It's the first execution didn't work out. No, you can't get to the heart within a fraction of a second without causing any undue pain or suffering, and then stop it and fry it. No, 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 because the heart is located deep within the body cavity. It's just the evolution, the survival of the fittest. That's where the heart needs to be. It's well protected. All right, that's the reason why whenever you're shocking someone using a defibrillator, you put in 20 amps of current. And from those people who have experienced it, that's the jolt that you feel and remember forever. Are you kidding? I mean, you're having a heart attack and they just jolt you, you feel it. It doesn't matter that 2,000th of a second, you will feel it. This is not a viable method of execution. But the idea is good. Idea is good. So the first attempt didn't work out. Did we abandon it? No. The heart should not be the main target of execution. The brain is. They changed it to brain. And I think that's brilliant in that sense that there's no consciousness lingering for 20 seconds at that point. All right, the heart of consciousness is the brain. All right, you hit it, it just wipes it out. You should not, in theory, you should not feel it. I don't know how you would test that, but in theory, you should not feel it. So they went from that, tried to target the heart initially, now it's the brain. All right, so here's what they do. Now this, I will have to give you a warning on this one. Okay, though it is a movie, it's the Green Mile, those of you guys have seen it. Give yourselves 5 points. I selected 2 scenes and carefully edited it. So you will only see the bad stuff. When I say the bad stuff, it's the bad stuff. Because now we have to discuss what's true and what's not. Okay, so we will have a discussion regarding how the modern executions usually take place. All right, so it's good acting, amazing special effects. I got news for you guys. The first time I saw the movie, I can watch these scenes. All right, because I've been lecturing on it forever. Right now, it's second nature. I know it's acting, but if this is the first time you will be seeing it, if you're not comfortable with it, just don't watch it. Just listen to me. Okay, so here's what I'm gonna do. I'll explain it as we go along. The modern executions. Okay, so it's a bunch of states still have the option to use the electric chair, and the details usually vary from state to state, but give and take, it's about the same. The amount of current that gets pumped into the body is about 20 amps initially. And how duration is, I don't know if it's 2 seconds, 4 seconds, or 6 seconds. I don't remember the details. It varies from states to states. All right, so you hit the body at 20 amps. The whole idea is to fry the heart, not to fry the heart, the brain, because the main organ, you can get to the brain immediately. It's right under the skull. All right, you just go ahead and boom, the person in theory should not feel anything. Okay, are you guys still here?
Yes.
Okay,
Yes.
cool. My voice is coming through because it says my internet connection may become unstable. Anyway, so you hit the brain immediately.
Everything's good.
Okay, good. So your brain gets hit immediately. At that point, you should be out.
It is breaking up.
Yeah, now you're silent.
So,
Yeah.
okay, cool. Okay, are we good now?
Yes.
Okay, cool. So depending upon the state, it's about 20 amps. Okay, it could be 2 seconds, 4 seconds, 6 seconds. It doesn't matter. In terms of seconds, it's no more than 8 seconds as far as I know, because or else the body can catch fire. Okay, the brain should be fried within a fraction of a second in reality. All right, so they go up to 2 seconds, 3 seconds, and then they go down to about 6 amps. The reason why they do that is because they don't want the body to catch fire. They also know that they need to actually stop the heart. Basically, that first 20 amp jolt may not be large enough, so they go down to 6 amps, maybe about 10 more seconds. Everything is done within 15 to 20 seconds. Once again, it depends on the state. At that point, there would be a doctor. Okay, they would check to see if there's a heartbeat. If there's still a heartbeat, they would do the second attempt. The first attempt at 20 amps, obviously the second one, they would keep it at 6 amps. Once again, it depends on the state. Okay, here's the problem. If the execution is done properly, the brain gets fried immediately within a fraction of a second. Okay, at that point, the theory is the person does not feel anything. But the heart, if the heart is not stopped, if it's not fried, it can keep up beating up to 20 minutes. You can literally cut the heart out, put it in a jar. It's an electrical organ. It can keep beating up to 20 minutes. And then again, how do I know that? Once again, we keep eating, guys. That's where I get my stuff. And the people who write it down, usually are experts, biologists. They do these experiments, obviously, the animal experiments, and that's what they came up with. So they have to stop the heart, and they will continue until it's done. Okay, so now that you understand what happens with varying details from state to state, let's take a look at the way it is presented in the movie. They will use a sponge. There's a reason for it. Remember the resistance of urine, 10,000 ohms. Mythbusters were using that as a uniform number. Okay, yes, that's not a uniform number. Skin has a tremendous amount of resistance. Skin's resistance is about it's 100,000 ohms. All right, the body evolved so that the body wants you to survive just about anything. I'll call it evolution. All right, so which means that you have to overcome that resistance. Just hitting it from outside, usually, like you get hit by lightning and people survive, and that's one of the reasons why. All right, because human skin offers tremendous amount of resistance. So what happens to the resistance of human skin? When you make it wet, it goes down below like 500, maybe 100 ohms. So it becomes highly conductive at that point. All right, so they will hit the heart, not the heart, the brain. All right, so they place one set of electrodes right on top of the brain. They want very little resistance between the brain and this because you don't want to cause any sort of pain, undue pain or suffering. That's the whole idea. All right, they cover the face because obviously things will happen. All right, from what I understand, the eyes bulge out, this and that. I don't know how much of it is true, but those are the stories that I find. The second set of electrodes will be placed on the legs. All right, so the current is going to go up and down through the body. That's the whole idea. And when the execution is probably carried out, you should hear this. Okay, the body does not react to it. It's going to hit the brain, boom. At that point, you're out. You're not going to hear a grunt. You're not going to hear anything. You will just hear a buzz. And obviously it's going to... All right, so this is kind of exaggerated. So it's just for special effects, just to get your attention. All right, this person is already brain dead at this point. The body heat up quite a bit. Doctor will check the heart. The heart is still beating. In this case, it's going to be beating, I think.
Again?
They will do a second one. It's usually at a lower current. All right, now this one is gruesome. Okay, this one is gruesome. This one is tough to watch. This warden, he's not going to wet the sponge. So he's got problems with the person who's being executed. All right, so this sponge goes right above the head. Because it's not wet, the skin is going to be dry. Sponge is going to offer a lot of resistance. The skin is going to offer a lot of resistance. So this person is going to take the current up through the leg. The last organ to be hit is going to be the brain.
Roll on 2.
This is very much similar to the first execution in history. So they will continue with the execution until the heart stops. All right, so that's probably inspired by the first execution in history. So could something like this ever happen in real life? It can. All right, if it's not properly maintained, if there's some bad connections here and there, it can go wrong and has gone wrong a number of times. Okay, so something like this can happen.
More than 4,000 men and women have died in the electric chair, which remains as controversial as ever. In 1997, a convicted murderer was put to death in Florida's 74-year-old chair. Witnesses saw flames shoot from his head, filling the room with the smell of burning flesh. Another inmate on death row appealed to the Florida Supreme Court, arguing it was cruel and unusual punishment. Court-appointed engineers examined the chair, known as Old Sparky, and proclaimed it to be in perfect working order, able to perform executions without causing pain or undue suffering.
Okay, so let's just talk about this, just briefly. Let's conclude this. So, can you kill someone without causing any undue pain or suffering using the electric chair? I got news for you guys. As bad as I made it sound, just executing someone is never a pleasant experience. This is a tricky business, guys. And when things go wrong, things can go wrong pretty badly, regardless of what kind of execution method that you're looking at. If it's botched, somebody's going to suffer. There's no question about it. If you can get to the brain within a fraction of a second and fry it, that's a viable method of execution. And most states will give you the options today. All right, they give you the options. If the electric chair is an option, there's going to be a second option. Okay? I will say, initially when I was teaching this, I thought this was a horrible idea, and over the years I evolved. Obviously, I mean, in terms of execution, if I'm going to be executed, I would go for it. Okay, because there's no such thing as remaining conscious for 20 seconds if it's done right. Okay, it would be boom, you would be out just like that.
Very similar words to those used by Thomas Edison himself.
All right, so the person behind the electric chair is Edison himself, the guy who gave us the light bulb. Okay, so one of the clarifications, Edison gets credit for the light bulb despite the fact that he's not the original inventor. This guy's a marketing genius.
A century earlier. For the History Channel, I'm Arthur Kemp.
It's kind of weird. It's worth discussing it, so we will discuss it in the future, I think within a few weeks. Edison is the guy behind the electric chair. He's the guy who made it possible for us to have the electric chair, despite the fact that he was completely against the death penalty. Okay, given the fact that this guy was against the death penalty, why did he push for the electric chair? Okay, so a lot of you guys thinking that, hey, maybe it's a more viable method of execution. No, actually, this is one of the things that he regretted for the rest of his life. All right, so what was the main reason for him? Okay, does anybody know? Okay, the reason why, people get into it later, I think it's going to be next week or the week after. It's because of something that happened between him and some other guy, Tesla, AC versus DC. We've been talking about direct current so far. Obviously, this is an application of alternating current. All right, the alternating current could be deadly or deadlier. And that was the whole thing that Edison was trying to prove. To what end is the discussion that we will have in the future. All right, so
Cliff Meidel expressing his gratitude to the men who brought him back to life. In 1986, while on a construction site, he accidentally jackhammered into 30,000 volts of electricity, 15 times the amount in the electric chair.
Most of the wounds were to my leg area, where I had a third of the knee joint burned away on both legs. He had 2 massive gaping holes in both legs. You know, surviving, I'm surprised. Not losing his legs, I'm stunned. The paramedics got back from the hospital and said that they actually revived him. Not only was I shocked, but I was almost wondering, you know, what kind of life is he going to live? It was a very difficult time for myself and my family. I was going to have my legs amputated, and it was the persistence of my mother and father to go out there and seek out a physician that would be able to save my legs. It was kind of a bleak time for myself and my family.
After 3 years, more than 15 surgeries, and against all odds, Meidel was walking without crutches.
At first, it was my dream to be able to run again, so that was kind of the driving factor for me to go into the gym, go to rehab, and keep pushing and pushing. And then I kind of found out that, I wasn't going to be able to run again, so I kind of thought, well, if I do sports that involve the upper body, I can maximize myself that way. That's why I got into kayak paddling.
Paddling became an integral part of Cliff's rehabilitation, helping to strengthen him physically and heal him emotionally.
I love challenges. The more effort that you put into the sport, the better the outcome is going to be.
Cliff's determination and passion led to an outcome that is the ultimate for any athlete, a spot on the U.S. Olympic team. He competed in the Atlanta Games in 1996 and again in Sydney in 2000.
Can you tell me why you love kayaking?
Yeah, I really enjoy kayak paddling because it allows me to get out there in the nature like we are right now.
Is it true the first time you got in one of these, you had to be carried to the boat?
Yeah, actually, when I started canoe paddling, before I got into the kayaking, the coach had to lift me into the boat because I still had crutches, and so...
Did you have any fear?
Yeah, I was afraid because I had these big knee braces on, and I was afraid that I wasn't going to be able to swim. I would just sink.
Right, you could drown. After everything you'd been through, now you're going to get in a boat,
yeah.
You can't use your legs?
I think that competitiveness and wanting to do it and be a part of the team kind of overcame those simple, basic fears of being able to swim. You guys got me out of the cardiac arrest and helped me progress in life.
These days, Cliff gives inspirational talks to firefighters, and especially to other burn victims, urging them to never give up.
You think that's why you were saved?
I don't know. My mother believes that. If I can help others, then I know I've done my job.
And he's just been named spokesman for the Construction Safety Council, hoping to lower the rates of electrocution in this country.
All right, so a couple of things about this guy. He would end up jackhammering into 30,000 volts of electricity and survived. Remember the guy ended up losing his arms because his bone marrow got fried? He said that he was lucky that the current didn't get to his heart and didn't get to his brain, or did it? Okay, once again, we got the same problem here. What's going on here? Why is it that that guy survived and why is it that this guy survived? All right, a couple of reasons for it. Let's run the numbers on this one. Okay, so I'm going to use the Mythbusters approach. I'm going to assume that the body has a uniform resistance. It's 10,000 ohms. Okay. And using the Mythbusters approach and using very basic math, which is the Ohms Law in this case, I'll come up with 3 amps. So the question is, can you survive 3 amps? You guys, assuming that that's 3 amps, the human body has a uniform resistance, which it doesn't. By the time the current gets to your heart, it's going to be about 3 amps. So what does it mean? So number one, this is alternating current. It takes 1 amp of current to stop the heart, obviously, and somehow this guy survives. Okay, so what makes it survivable usually is the duration. Okay, and then this guy had a long enough duration. And if these are the actual numbers, he wasn't supposed to survive that. Instead of having a heart attack, he should have been dead, depending upon the duration of it. 3 amps of current, it's like 1 amp of current is what you need to get to the heart. If you're on the electric chair, obviously, these numbers don't make sense. So what I'm going to do is I'm going to take a little bit more realistic approach. Human body, this skin's resistance is 100,000 ohms, so that's the number that I'm going to use. Now you're looking at 3/10 of an amp of current. All right, so this is large enough to give you a heart attack. All right, so if this is the amount of current that gets to the heart, obviously duration matters. In this case, there was a long enough duration. This guy was literally having a heart attack. All right, so all of a sudden we got a big picture. All right, so the other guy ended up losing his arms. He wasn't exposed to the current. It was just a flash. All right, he got zapped pretty badly. The bone marrow ended up getting fried. Muscles are okay. The muscles are okay because the muscles are electrical organs. They're good at conducting current. Bone marrow is highly resistive, so it ended up frying, ended up heating up. So the power was lost through the bone marrow. And then if the current got to the heart, not a big deal. All right, once again, it's just a flash injury. If the current was more than an amp, what happened? It just jump-started the heart. If it got to the brain, once again, the duration wasn't long enough. The current wasn't strong enough to actually fry the brain. Either way, the guy survived, and you can't survive something like this. So that explains what happened to the guy who ended up losing his arms because of amputation. And what happened to this guy was he was having a heart attack already, and they were able to actually stop it. All right, so the distance matters. Obviously, he took the current up through the legs, all the way to the heart. So regardless, it was within the range where he could have died from a heart attack, and he didn't. He did survive. All right, so the next question is, given the fact that the heart is right in between the arms, remember the guy whose arms were amputated? Heart is right in between the arms, obviously. So why is it that heart got hit? Why is it that the brain also got hit? The brain is kind of out of the way. So what's happening in terms of that? So the way everything is connected is going to matter in terms of resistance. When things are connected in series versus in parallel, something that we discussed before. So we'll have a formal discussion on that one. All right. So defibrillating the heart. Somebody's having a heart attack. What do? We pump about an amp of current into the heart in order to stop it. So into the chest cavity, they put in about 20 amps of current within 0.02 of a second. All right. So the timing is important here. It's about 1,000th of a second. You don't want to make it any longer. You want to stop the heart and jumpstart it. If you make it longer, you can fry the heart. So how do they control the discharge time? So the time of discharge is crucial. So we talked about how they store the charge inside a capacitor. Now we're talking about controlled lightning in essence. So how do they control this? Now it's important in terms of multiple flash photography or this kind of photography that you're looking at. Notice that the controlled discharge is microseconds here. It's like a millionth of a second. All right, so we're still discussing direct current circuits. So the current is going to be coming out of a battery. Each and every single appliance that you can hook onto the circuit is going to offer its own resistance. And we got two connectors like that. So what happens to the overall resistance? So we had a short little discussion about it last week. It's almost like a traffic flow. You get an accident, red lights, someone not moving at the speed limit. So what happens? The resistance is going to go up. Overall resistance is going to go up. So we end up adding the resistance values directly in essence. All right, so it's the same current that's going to flow through each and every single resistor. The resistors could be appliances, so which means that they could be artificially introduced into the circuit. Or you may have resistors, which will offer a certain amount of resistance so that you can control the current flow. All right, so this is the Ohm's law. All right, so this is the amount of voltage which is going to be supplied by the battery. And it's going to be exactly the same current, which is going to be going through each and every single resistor that we got. So this is the total voltage supplied. And so this is the amount of energy supplied to the circuit by the battery that we're looking at. All right, all three of them have the same resistance value in this case, which means that the voltage is going to be evenly divided. In reality, the voltage drop across each and every single resistor depends on the resistance value. All right, so the voltage drop represents how much of the voltage is going to be lost through the resistor or lost in the form of heat or light in this case. All right, so the overall voltage supplied by the battery is going to be equal to the total voltage drop across each and every single resistor. This comes out of the conservation of energy principle, something that we discussed before. So we will just sum up the voltage drops across each and every single resistors that we got. So here's the voltage drop across the first one, the second one, and the third one. And notice that all of them will have the same current running through them. All right, so the current across the first one, the second one, and the third one will be the same because it's the same current. All right, so here's the voltage supplied. This is going to be the voltage drop. They will be equal to each other. Here's the resistance, okay, and this represents the total resistance of the circuit, and this represents the total current going through the circuit. So obviously, the total resistance is going to be the summation of all the resistance values that we got, and that's it. All right, so if it is a current going through each and every single resistor, if it's the same current, because the resistors are connected in series, what you do is you just sum up the resistance values of each and every single resistor. All right, so what's going to happen is because the resistors are connected in series, the overall resistance is going to go up, right? So A is the best answer, so give yourself 5 points for that one. Take that one. All right, so problem number one is straightforward. I'm not going to do the problem, but let's take a look at it. Anyway, it's straightforward. All right, so what you need to do is just figure out the overall resistance of the circuit. So the overall resistance is just sum them up. This plus that, this is going to give you 9 ohms. If you know the voltage, if you know the resistance, you can figure out the current. And you can also figure out the power dissipated in each resistor. All right, guys, I have the solutions for these. Just look them up. That's straightforward. All right, resistors connected in parallel. So all of them are connected in parallel. So what's going to happen is, once again, it's like the traffic flow. We discussed that. The shortest path is this. You're leaving work, trying to get home. Except there's a bad accident here, so it's going to offer a lot of resistance. So you're going to go up to the next intersection. Some of the traffic is still going to flow here, and the remainder of the traffic is going to go up to the next intersection. There are a bunch of lights here, so it's not to your liking, so you go up to the next one. All right, so because the current is given multiple paths, the overall resistance is going to be lessened, which means that it's going to be overall resistance is going to diminish in essence. Okay, one of the things that you need to know is the voltage supplied is going to be the same as the voltage drop across each and every single resistor. All right, so that's what they have in common here. All right, so that's going to become our setup. So the voltage supplied by the battery is going to equal to the voltage drop across each and every single resistor. Current is going to split at every single junction point. Our junction point is where the current splits, obviously. Some of the current is going to go this way, the other current is going to go that way. So the current is going to branch out 3 ways in essence. So the amount of current supplied by the battery and the amount of current which is going to branch out will be equal to each other. Right? So the summation of all the currents will be the same as the amount of current supplied by the battery. So this comes out of the conservation of charge principle, the law of conservation of charge. All right, so the current supplied by the battery is going to be the same as the current going through each and every single resistor. So the current going through the first resistor, the second resistor, and third resistor is going to be that. The voltage drops across each and every single resistor is going to be the same as the voltage supplied by the battery. So we end up getting this generic expression. And then since this generic expression can be expressed in terms of the Ohm's law, all right, so this is going to give you the total resistance. So the total resistance will be computed as reciprocal resistance of the summation of all the resistances within the circuit. So when you plug the numbers in, you will notice that the resistance goes down. When the resistance goes up, goes down, the current goes up. Okay, work on it on your own. All right, let's take a look at problem number 3. All right, so we got the combinations of resistors. So how would you do a problem like this? All right, so I'm not going to be interested in numbers. I just want to show you a couple of things, in terms of doing these problems. All right, so number 1, there's a junction point here. So which means that when current gets up to this point, it's just going to split. Part of the current is going to go this way, part of the current is going to go that way. What that means is because the current splits, this portion is going to be parallel to that portion. Okay. And notice that it's the same current that's going to be going through this resistor and that resistor, so which means that these two will be in series. Okay. Because these two are in series, so what you do, you just sum them up. So these are going to be summed up. And then the summation of these resistor values will be parallel to this one. So now you have to add them up inversely, reciprocally. All right. And then all of a sudden, this junction is going to disappear. Obviously, this becomes in series with this one. The combination of these three is going to be right here. And then so you will just sum it up. Here's what I'm talking about. The first thing I would do is just sum up these two here into a single resistor. Okay, so there's a junction point here, which means that the current is going to split. Now, what you need to do is these two are in parallel. So now you have to sum them up reciprocally into one single resistance. Okay, at this point, it's the same current which is going to be going through this and that. So these are going to be in series. So which means that you got to sum them up directly. So this plus that is going to give you the total resistance of the circuit. All right, so how it is done. All right, so we discussed this before. The household circuit is going to be connected. Pick out the best answer for this one. All right, so the best answer is going to be D, right? All right, so the best answer is going to be D. So you can turn on and off appliances without shutting off the circuit. That's the whole idea. All right, so defibrillating a heart, 20 amps of current pumped into the chest cavity within 2 thousandths of a second. All right, so this is the amount of energy gets transferred, electrical energy. And that's everything is expressed in terms of power. All right, so the only thing that I'm interested in right now is how do we control the duration of the discharge? How do we control the duration of the discharge? And once again, the same question goes for this one. How do we control the duration of the discharge? Here it's going to be 2 thousandths of a second. Here it's going to be less than a microsecond, millionth of a second, less than a millionth of a second. Okay. The way we control these are known as RC circuits. Circuit is going to have two components. It's going to have a resistor. It's also going to have a capacitor. So obviously, we're going to charge up the capacitor. And the resistor actually is what controls the timing of it. You can charge it up and you can also discharge it. So this is a capacitor which is being charged up. It's being charged up gradually. So the voltage is increasing across the capacitor gradually. That's what it means. And this represents the discharge. The voltage across the capacitor is decreasing, once again, gradually. Okay, so what allows you to actually control the charge and discharge times is the amount of resistance that you have. Also, it depends on the capacitor. So it depends on two things. So you can charge it up and you can also discharge it. You can charge it up in a controlled fashion and you can also discharge it in a controlled fashion. Okay, guys, it's the same as controlling lightning in essence. All right, so you can charge it up real fast and you can discharge it real fast, or you can charge it up slowly and discharge it real fast. You can just control it any way you want. So the question is, how do we do that? Okay, so how do we do that? Okay, hold on. Okay, so we will kind of ignore the detail of the math because this is intended for university physics students. University physics is engineering physics. All right, you guys are taking college physics. That's algebra and trig-based physics. Okay, so just ignore the details for now. What I'm doing is, okay, so we throw the switch on, so we will just charge it up. All right, so this thing is charging up, and we'll just skip through the mathematics. All right, this is known as the Kirchhoff's rules, so I just want to keep moving in the forward direction. Turns into a differential equation. All right, so this is as far as I want to go. All right, so we skip the math, and this is where we're at. Okay, so I'm going to be interested in the meaning of this formula. Okay, so this is a charge-up equation. All right, so this equation represents that the capacitor is charging up. All right, it's charging up and it's charging up gradually. All right, so when you see this equation, that's the meaning of this equation. Okay, this Q naught that you're looking at is the maximum value that it's going to get charged up to. All right, so you got 1 minus E to the power of minus T RC that you're looking at. All right, so this equation, when plotted, it's going to look like that. So this equation represents charge up of a capacitor, charging up of a capacitor. Okay, so T is obviously time axis. Q represents the net charge. So the net charge is going to build up this maximum value. This is what it represents. Okay, so in the exponent of the exponential that you're looking at here, you have the time divided by RC. Okay, when you're looking at an exponent, any sort of exponent, these need to be unitless. Okay, that's one of the things that I want you to remember. Time is going to have the units of seconds. RC should have the units of seconds. The R is the resistance, obviously, and C is the capacitance. But because of the fact that the power of an exponent or anything has to be unitless, this is known as the capacitive time constant. All right, so the resistance and the capacitance will multiply together. It's known as the capacitive time constant. Okay, therein lies the answer to our questions. How do you control the charge up period? How do you control the discharge period? All right, you control it by controlling the resistance, and you control it by controlling the capacitance. All right, so this is the Greek letter tau that you're looking at. It's not T, it's tau, or in Greek letter, it's tau is T. All right, it's known as the capacitive time constant. Okay, what it actually represents is it represents the amount of time it takes for it to charge up to 63% of its maximum value. Okay, so that detail is not that important. All right, you're not physics students, engineering students, just ignore it. Just remember, it controls how fast something is going to charge up, how fast something is going to discharge. Okay, that's a better description than just something real technical, which is not going to mean anything to any of you guys. All right, so capacitive time constant tells you how fast it's going to charge up and how fast it's going to discharge. All right, so what that means is if capacitance, okay, so let's just talk about that. If resistance is large, it's going to take longer, right? If its capacitance is large, it's going to take longer. I mean, if it's got a high capacitance, which means that it can store a lot of charge, it's going to take a while for it to charge up. It's almost like capacitance like a bucket, right? You're going to put water in it. All right, if it's a small bucket, it's going to fill up real fast. If it's a big one, well, you got to wait for a while. All right, so the larger the capacitance is, the longer it's going to take for it to charge up. Larger the resistance is, the longer it's going to take for it to charge up. All right, large resistance will delay it. A large capacitance is going to delay it. That's what it means. So if something is charging up, use this equation. That's all you need to know. All right. And larger the resistance, longer it's going to take. Larger the capacitance, longer it's going to take. All right, so capacitive time constant represents how long it's going to take for it to charge up. All right, now we're focusing on we're going to be focusing on all right, so, okay, we talked about the capacitive time constant. Okay, so the next one is the discharge equation. All right, so we'll skip the details, just move to the very bottom. Okay, once again, the equation looks like that. All right, so Q naught represents the maximum charge stored inside the capacitor. And this represents a discharge. This is an exponential decay that you're looking at. So now it's discharging. Okay, RC once again is going to represent the capacitive time constant. It represents how fast or how slowly it's going to discharge. Okay, once again, larger the resistance, longer it's going to take, larger the capacitance, the longer it's going to take. All right, so if it's a discharge, use this. And if it's charging up, use that equation. All right, so those are the differences. Okay, in terms of algebra, we got to do a little bit of algebra at this moment, because most of you guys kind of out of practice. Even the engineering students tend to be out of practice at this point. So what I'm going to do, I'm just going to do a little bit of algebra so you guys know how to actually isolate the unknown. Okay, so when at the rate it charges up, the potential within the capacitor is going to increase or decrease at the same rate. All right, we will get to use the same equations for both of them. All right, so the capacitor charges up, and then the voltage goes up inside the capacitor at the same rate. So the equations will look the same. All right, so I usually focus on the charge equation. So this is the maximum value that we're charging it up to. That's the meaning of it. So, or if in terms of the voltage, all right, guys, one of the things that I should mention at this point. V represents voltage, and epsilon, the Greek letter epsilon, also represents voltage. This is known as electromotive force. Okay, so it's, if you see the symbol, that's what it means. I'll reiterate it in the future. So epsilon naught represents the voltage again. All right, so imagine that you have this equation, one on top, and then imagine that you're trying to figure out the resistance. All right, so how would you isolate resistance? Okay, so this is the algebra review that I'm going to do for you guys, because if you've done this sort of stuff, it was in high school and it was probably quite a few years ago. You wouldn't remember something like this, or at least most of you guys would. Anyway, so I'm going to try to isolate R. I notice that's the power of the exponent. So I need to get the exponential term all by itself first. So get rid of Q naught from both sides. And then I usually move things around. I want to have my unknown on the left-hand side. So I'm going to move this here. So negative becomes positive. I will move this there, and this positive becomes negative. So the equation looks like this. Okay. Another thing that I'm going to do is I don't like to have a negative power because it makes things complicated. So what I'm going to do is I'm going to invert both sides. All right. So I'll take a shortcut and I'm going to invert both sides. Negative is not a good thing to have. So what I'm doing is I'm inverting both sides, which means that both sides will get divided, inverted. That's what it means. All right, so that's the meaning of that term. I'm inverting both sides. All right, so this is a power of a power, so this time this is going to be positive, and which means that this becomes a denominator on the right-hand side. All right, now that's what I did. Okay, the next thing I'm going to do is I'm going to get rid of E by using an inverse function of E, which is going to be ln. So I'm going to take the ln of both sides. All right, so that's it. All right, so E and ln are inverse functions, so which means that they will cancel out. So which means that the only thing which is going to be left over is the exponent, the power of the exponent. So it's going to be t divided by RC. The term on the right is going to remain as is. I'm going to break it down. So it's going to be ln 1. The expression inside the denominator can be expressed in terms of a negative of the ln. All right, so this is what we end up getting. All right, so natural log of 1 is going to be 0. I wonder if I'm going to carry. Yeah, okay, I do carry it. Wow, that's the. All right, and that's it. Now you can isolate R from here. So I got my own way of doing it. So there's a multiplication. So I can grab this and then the entire side, and then I can just switch those two. All right, so I came up with my expression. So this is the final expression for that. Okay, guys. If you were barely able to follow this, if that's the case, you have to practice it. Okay, you have to practice this until it's second nature, because something like this would be a good test question. All right, what I'd like you to do is I want you to repeat this while you're studying for the test. Make sure that you can step through it properly. Okay, I solved it for R. In your case, try to solve for C, and then try to solve for T. All right, if you can do those, then obviously you can handle it. All right, so let's do a simple problem. So problem 8 is the one that I'm interested in. All right, notice that this is discharging. All right, so which means that we have to use a discharge equation. It's an RC circuit. The reason why I know that, not because of the title, it's got a capacitor connected to a resistor. This resistor has a huge value. All right, so it says the capacitor loses 63.2% of original charge in 8.3 seconds. This should be lost. Okay, what is the capacitance of the capacitor? All right, let's back up a little bit. So that's problem number 8, right? Let's back up. Okay, so what do we have? This is problem number 8. This is already charged up to this value, right? So what's happening? It's discharging. It's discharging within 8.3 seconds through a resistor, which has a tremendous amount of resistance. Okay, so what do we want? We're looking for C. So what is this capacitance? So this is the formula that we pick because it's discharging. This formula represents this graph. All right, so it's an exponential decay. All right, so what's given to us is, okay, so let's get back to the terminology on this one. 63.2% of its value. Right. Okay, so the capacitor lost 63.2 of its original charge. Capacitor lost, it should be lost, will lose 63.2 of its original charge. Okay, so if it loses 63.2% of its original charge, okay, so if it loses 63.2% of its original charge, the 63.2 divided by 100, guys. This represents the leftover charge, right? 1 minus 0.06 is going to represent the current charge. All right, so that's the reason why 1 minus this is going to represent the current charge. So the current charge is going to be here somewhere, measured with respect to the lowest point. All right. All right, so having said that, that was a bit of an explanation. Once again, you have to kind of think about it. Just listening to me talk is not going to help. You have to convince yourself that that's the case. All right, so the next thing is isolate C. I'm going to get rid of Q naught, the maximum charge. Okay, so I'm going to employ the same trick. I don't like having a negative here, so I'm going to invert both sides. All right, so this side gets inverted, so negative times negative is going to be positive. All right, and this side, you just invert it, so Q naught divided by Q is what you end up getting. Okay. Next thing is you have to do is now you have to get rid of the exponential term by taking the natural log of both sides. All right, so this left-hand side is going to be T divided by RC. On the right-hand side, this is going to be the same as that. Okay, so what are we isolating here? We're isolating C, right? Okay, so if that's the case, I'm going to switch this by C. So it's going to be T divided by R times ln Q naught Q. And then I'm going to express Q in terms of Q naught. All right, so the Q naughts will cancel. And then you plug the numbers in, and then you'll get something for it. All right, I didn't plug the numbers in. Okay, so what drives current is, okay, a number of things. The simple answer is the voltage difference. Voltage difference implies that where the current is happening, it happens in between two opposite charge regions, right? That's the reason why there's a voltage difference. Voltage difference means that the field, the region between two opposite charge regions, the area between two opposite charge regions is energized, which means that there's an electric field pointing from one high voltage region towards the low voltage region. High voltage region is positive charge, the low voltage region is negative charge. If there's a potential difference or voltage difference, that implies that there's electric field. You know, the electric field is an electrostatic force field, which means that it's got energy stored in it. All right, so the more energy is stored in the electric field, more the faster the charges are going to move, because the electric field acting on the charge is going to induce a force on it, and because of the force, the charges will accelerate. Okay, so it's blah, 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 blah. Short answer is, what drives current is the voltage or voltage difference. Okay, so how are electrons replenished inside a metal conductor? We're talking about a wire in order to sustain current. Okay, so electrons are replenished usually by providing electrons to a negative charge region or a terminal through chemical reactions inside an acid solution. Okay, so that's what the battery does. Okay, that's known as a battery. Resistance is whatever resists the motion of charges. Resistivity is how much the atomic or molecular structure resists the motion of these charges. Resistance is directly related to resistivity. More the atomic or the molecular structure resists the motion of the charges, the larger the resistance is, obviously. Resistance is going to be directly related to length. Resistance is going to be inversely proportional to the cross-sectional area, meaning that the thicker the wire is, the lower the resistance is going to be. Resistance is directly related to temperature. The hotter it is, the larger the resistance will be. What caused the temperature of the wire to rise is the random vibrational as well as the rotational motion of the molecules. What caused molecules to vibrate is the electrons colliding with them. All right, so what happens to current when the resistors are set in series? Okay, so when the resistors are set in series, what happens is the overall resistance of the circuit goes up, the current goes down. Okay, guys, resistance is what resists the motion of the charges. Larger the resistance, slower the charges move, smaller the current is. What happens to current when the resistors are set in parallel? When the resistors are set in parallel, the overall resistance of the circuit diminishes. As a result, the current goes up. So when the resistors are set in parallel, overall resistance diminishes, it goes down. As a result, the current goes up, so current increases. What's power? General definition of power is how fast the work is done, how fast the energy is transferred. In terms of electricity, power can be lost as well as the gain. So power generated means how fast the chemical energy gets converted into electrical energy. Power lost means how fast the electrical energy gets converted into heat and or light. All right, so explain where the energy comes from when the power is generated. It comes from a battery. So how fast the chemical energy gets converted into electrical energy is power generated. Explain how the energy is lost, given that the energy can neither be created nor destroyed. So the energy lost is the electrical energy is being lost. The lost energy is going to appear in the form of heat as well as light. So what's the purpose of the third prong is to ground the device. All right, so the third prong is used to actually ground the device. The devices that need to be grounded tend to have metals they tend to be metal casings. All right, the reason why that happens is because they need to be grounded, because in case there's a loose wire touching the metal from the inside, the electricity is going to be on the outside. All right, so if you come in contact with the metal casing outside, you will become part of that circuit. You will get shocked. That's what it means. Okay, so how does the grounding wire work? Obviously, that's going to be a test question. Grounding wire is going to set up a circuit that becomes parallel to your body. All right, so given a choice, the current is going to go through the grounding wire to the ground rather than going through your body, because your body offers a lot more resistance than the grounding wire does. 65 milliamps of current, would that be large enough to kill? It would be large enough to give you a heart attack. So it can potentially kill you, yes. And 65 milliamps of current is the amount of current that would be going up the urine stream if you were to piss on a third. I was going to say the third prong. Forgot the name of it.
Third rail.
Third rail, yeah. It's a long day. Yeah, give yourself 5 points. All right, so what's the biggest difference between accidental electrocution at home and the electrocution in an electric chair? All right, number of differences, guys. Accidental electrocution at home, the amount of current is relatively low. It's not meant to be deadly. If you come in contact with the current, it doesn't do any harm. The problem starts if you somehow grab the wire and if you cannot let go. That's when the problem starts. When you grab the wire and then your hand paralyzed around that, you become part of the circuit, you cannot let go, and now you got problems because now the current is free to travel anywhere in your body. All right, it gets to the lungs, obviously you're going to have a hard time breathing. If it gets to the heart, it gives you a heart attack. All right, so heart attack is what kills you. It's accidental. the amount of current is usually not large enough to kill someone instantaneously. And most people, usually they touch it with the outside of their arms, the hand, or whatever. Immediately when you notice that something weird is happening, you reflexively you pull away. That's what happens to a lot of people. But by accident, if you just grab a live wire, you're not. If you cannot let go, obviously that's when the problems happen. All right, that's the accidental electrocution. All right, the execution, electric chair, the execution style is different. The amount of current is meant to kill you. Usually it's more than an amp of current which is pumped into the body. It's about 20 amps. All right, the target organ is usually the brain. You want to hit it immediately within a fraction of a second. It should not cause any undue pain or suffering in theory. I don't know what the actuality is, obviously. And at that point, that's it. And if it gets to the heart, you want to have more than an amp of current to stop the heart and keep it there long enough to fry it, because you don't want the heart to beat. All right, so the difference is in the accidental, the amount of current is really low. And what kills you is because you become part of the circuit and your hand paralyzes around the source. You're not able to let go. And in the case of the electric chair, that's a tremendous amount of current. It's 20 amps of current pumped into the body to destroy the brain and destroy the heart at some point. Okay, so why do they apply more than an amp of current to the heart if the heart is fibrillating, which means if somebody's having a heart attack? The reason why they do it is because heart is an electrical organ. It's like an electrical device. It resets itself. Okay, if it's just beating irregularly, what you do is just stop it momentarily, fraction of a second, and then it resets itself. It regains its natural rhythm. All right, so that's the reason why they do it. So amp of current is necessary to freeze the heart, in essence, or stop the heart. Okay, so what's the capacitive time constant? The capacitive time constant tells you how fast, it tells you about the amount of time it takes for the capacitor to charge up or discharge. Okay, that's the meaning of it. Capacitive time constant is the amount of time it takes for a capacitor to charge up or discharge. So what does it represent? Well, 21, just skip it. It represents the amount of time it takes for it to charge up to 63% of its maximum value. But that's not that important. All right, so the capacitive time constant is a combination of resistance as well as capacitance. It's a combination of both of them. Okay, so let me just backtrack here. So what it is, it's a combination of resistance and capacitance. Okay, so you get a multiplier. It's a product of capacitance and resistance. What does it represent? It represents how fast or how slowly the capacitor is going to charge up or discharge. Okay, so that's what it is.